Good morning once again, everyone, and welcome back to our lecture on human population and environmental bioethics. Today's lecture is on energy. So we begin, as always, in the name of the Father, the Son, and the Holy Spirit. Blessed Trinity, we love you, we adore you, and we thank you for your many blessings. We ask that you be with us now, inspire us, continue to inspire us so that we may live according to your divine will in a very special way, to be able to live with nature, the nature that surrounds us, to use it responsibly and wisely so that we don't destroy it and end up destroying ourselves in the process. We know that you're with us every step of the way, and we continue to pray in a very special way for those who are in most need of your divine mercy. In the name of Christ, our Father, Son, and Holy Spirit. Okay, anything from previous classes? Questions?
I review everything.
Yeah?
I review everybody the videos in my house.
Yes?
Especially for the recycle.
Right?
Yeah.
Yes.
Very clear what exactly we should do. I have my mother-in-law at home, so she's the one who always put it this time.
There you go.
So
She's in charge of collecting.
Everybody's on the same page now. We understood, and it was very interesting to watch the videos.
Good. I'm glad. Yes. I think that at the level of each individual consumer that we are, right? In contemporary society, you're born into this world and you become a consumer.
I have so many public bags and supplements. So I said, we're going to start using seriously.
Right. The bag that the reuse.
The
reuse.
The reuse bags. You know, the green one. And the,
right. There are cloths.
I have so many, but we never use it. We always, I forget it, so we bring plastic bags again.
Exactly. Just throw them in the trunk of the car, the empty ones, and keep some in the trunk, keep them upstairs.
Well, and say one of the things that's happening now in Coral Gables is that the public's no longer.
I'm sorry. Let's have one conversation at a time. I'm sorry.
Yeah. I would say in Publix in Coral Gables, we no longer give plastic bags. They have to get it, and that's something that I know is going on in California.
Yes.
But Coral Gables, the city passed an ordinance, no plastic bags, and they were giving out, I think, one.
Oh, yes.
A couple of weeks ago to get everybody.
One for free, right, to get you started. All right, that's an incentive. Yeah. Okay, you were saying, Carola?
No.
Yeah, go ahead. Go ahead.
No, como usted decía, I'm sorry.
Sí.
We have to refill the bottle of water again.
Right. Yes. So I think, again, at the level of individual consumer, right, aside from whatever we could do professionally, if we are in charge of a sector of a company or something like that, or even in an education setting or in industry, at the level of individual consumer at home, in residence, the residential aspect, certainly that recycling and what should and should not go into that bin, because that makes the system more effective. And those three little words, remember, reduce, reuse, and recycle. The three Re's. Reduce, so try to use less, right, or whatever. I think I was watching a little video from Cardinal, it's a Cardinal in the Philippines. I forget his name, but he's a young fellow, and he says, try to live a simpler life. Try to live a simpler life. Don't get so complicated, all right? So that's with regards to reduce. Reduce, reuse. So reuse that cloth bag instead of getting a disposable thing. And then recycle. And those are the three. It ties it in with a bigger picture that we'll address more fully at the last class, which is that of all the living species that exist on Earth, we're the only ones that produces overabundance of waste, right? Every other plant, animal, fungus, bacteria produces waste that is recyclable and actually keeps the system going. And when they die, they get recycled themselves. So it's 100% recycling in the rest of nature.
So I heard in your recording that we are producing 4 gigatons extra of CO2.
Yes.
Uh-huh.
We bring it down to that, to the most wasteful element right now, or compound, if you will, by weight and by impact on the environment, is CO2.
For industrialization and all that.
Yes, because basically it's a byproduct of burning. And burning, even we'll see recycling today in more detail, all right? And also energy production. Typically it involves burning. And one of the byproducts or end products of burning is CO2. So what to do with that darn CO2, which happens to be a greenhouse gas.
And that's what we call it warming.
And that is increasing the global warming.
The temperature.
Yes, because it's a greenhouse gas means that it retains heat, just like water retains heat also. So water vapor is also a greenhouse gas, for that matter, water vapor. But of course, water doesn't become vapor until it's 100 degrees centigrade. But CO2 is gas at a lower temperature.
That is related with the ice cap melting or something?
Yes, it is. We'll take a closer look at that, but that's related to that, yes. Because it's increasing the temperature of the atmosphere of Earth all around. Slightly, but really, all right? So there's one thing that we have to understand in nature is that every niche that can be taken up is being taken up, all right? Or will be taken up. For example, if we abandon this building, just as a drastic example, let's say that for whatever reason, the university closes, this building is abandoned for X number of years. What's going to happen to the building physically? It's going to start, yes, decaying, and it's going to start being taken over by nature. Before it actually falls down, which if we give it enough millennia, it will fall down because of erosion, right? Because of the abiotic factors. Mostly light and rain will start breaking it down, and that will take millennia, just like we have ruins that are thousands of years old. But way before that, within a few short years, this would just be covered with plants and algae and bacteria and fungi, right? First on the outside, and eventually they'll work their way inside too. So these are, all these surfaces are potential niches for nature to colonize, to take over, all right? And it's a very narrow margin, if you will, where plants and animals and living things live. It's a very narrow margin, okay? So that if there's a change in temperature or climate, then the species will change, because some species are better adapted at a colder climate, other species are better adapted at a warmer climate. A similar argument can be made also for abiotic factors, and particularly for water in the 3 states. So the amount of ice that we have right now, natural ice on Earth, which is the bulk of the natural ice on Earth right now? 2 regions, specifically. The 2 poles, right? That's where we have the bulk of the natural ice on Earth. All right, and it's also the bulk of fresh water on Earth. It's in solid state. It's not it's not in liquid. The second group, if you will, of ice on Earth, of natural ice, which is much smaller by volume, but it's real, is going to be where? In the glaciers and snow-capped mountains. The mountain ranges, the large ones, above 10,000 feet on average, the Andes, the Alps, the Rockies, the Himalayas, I think those are the main ranges, okay? But by comparison, that's a very small amount of water there in comparison to the ice caps. So the bulk of the water on Earth of fresh water is taken up in the ice caps. With a slight change in temperature, that ice cap will either increase or decrease if the temperature goes down or up. All right, so if the temperature goes down, lower, the ice caps will increase because there is snow falling on them. And if the temperature decreases, that snow will stay there longer and eventually will compact into what becomes ice, solid ice. But the opposite is also true. If the temperature increases, it starts melting around the edges, and then those ice caps begin to reduce. But the water physically, materially, is still on Earth. It just goes from solid to what? To liquid. And it's going to go where? Into the oceans. Now the oceans are vast, but they are a basin, right? So, and the edge of that basin is the shoreline around all the continents, which, by the way, the shoreline is at certain different levels, right? The Atlantic Ocean, even the North Atlantic, the South Atlantic will be at slightly different levels, even though those volumes of water are all connected. All the oceans of the world are interconnected, all right? But they're interconnected through discrete areas, and it takes time physically for that water to move such a huge volume back and forth. Also, they're influenced by the tides differently. They're influenced by the gravity of the moon, which is what causes tides. Different because the larger the volume, the more overall pull and the bigger the tide. So the Pacific has bigger tides than the Atlantic. That already is making a difference at the sea level. I'm kind of focusing on the sea level and the surface on shorelines. But anyway, as that solid water is melting, is going into the oceans, then that volume has to increase. It cannot increase downward because there's a bottom, even though there is percolation into the crust, and there's circulation of seawater through the crust. All right, there's a recycling there also at the bottom because the bottom is not impermeable. It's semi-permeable, so some water does percolate inside and seeps through and recycles. But the bulk is going to go to increase the volume, to increase the shoreline, all right? The sea level, so that's called sea level rise. And that's being detected slowly but surely around the hemisphere. The problem is that it's a relatively short period of time so far, maybe a decade or so, maybe 2 decades, it's hard to tell. But there is a gradual but real increase. Then you consider that many, many people throughout the world live along the shoreline, especially in the southern hemisphere and in places where it's easier to make a living near the shoreline than inland, right? In more primitive economies. So that's going to impact them generally negatively because you're going to get saltwater intrusion, right, into fields and things like that. If you get saltwater intrusion into a rice field, the rice field is gone. Might as well become a mangrove swamp. Okay, so it can change drastically the economy of certain populations. Typically, the populations that are higher risk are the poor populations, and that's why the urgency of Pope Francis with his encyclical, tying in the environment with the poor, all right? So connecting dots. Anyway, this issue, we'll revisit it, especially in the last class, when we'll do another roundup, okay? Group dialogue. What I wanted to clarify some things that I've said before, and I've noticed I've made some mistakes in some things that I said, so I want to correct. I found 3, well, one mistake, one that I'm not sure that everybody understood, and then one that I neglected to mention with regards to the atmosphere. All right, we're talking about the gases. The color of the sky, which I thought was a reflection from the ocean, it turns out it's not. I made a mistake there. It is actually essentially the same phenomenon. It's light, white light, filtering through the atmosphere. But because the atmosphere, so two things. First of all, water, liquid water, the oceans it's a fluid, right? It's a fluid. But the atmosphere is also a fluid. It's a gas, but it's a fluid. So it's a thinner fluid, less dense, but it's a fluid. And therefore, when light goes through a fluid, it diffracts, whether it's in the ocean, in fresh water, or through the atmosphere, or through any gas, all right? So essentially, we have the same prism effect. White light, which remember is, as far as the wavelength, is the dirtiest light because it has all the wavelengths together. When it goes through a fluid, that fluid acts as a prism. So it decomposes the light into its colors, its primary colors, the rainbow, what we call the rainbow. So that happens in the ocean, but then the wavelengths have different lengths. That's why they're called wavelengths, all right? So the higher wavelengths are the ones that penetrate deeper, and those, it's in the blue range, blue and violet, but mostly the blue range. And that's why we see the ocean mostly as a blue color, because the red and the infrared get filtered out in the upper layer of the ocean. We get a similar effect with the atmosphere, but because the air is thinner, then the diffraction that it causes is a lighter, and that's why the sky is a lighter blue than the ocean, because it's less dense, all right? So gas is less dense than liquid, but it's still a fluid, and that's what's causing that diffraction. So we also get a diffraction. And that's also why we get a rainbow when it rains. What happens is the actual rain, the water, liquid water, is acting as a prism through the atmosphere, and it decomposes the light again, but the liquid water of rain is denser, is more dense than the atmosphere through which it's traveling. And then one final detail, since on the rainbow, so you notice the rainbow is the actual decomposition of the white light, okay? That's why you don't get a rainbow at night, for example, because there's no source of white light. There's no source of light coming from the sun. And then the last detail, why the rainbow is circular, because precisely it is reflecting or following the path of the atmosphere, which is circular. So that's why the rainbow is circular, because it's also following the path of the circle of the atmosphere, of the sphere of the atmosphere, okay? So that's one correction I want to make. The detail, but I want to keep it true. The other one, that from reading your summaries, maybe I made a mistake in saying it, or maybe I was not clear with regards to the relationship between temperature and pressure on gases, on air and gases, right? It's part of what is called the gas laws. If you remember your physics from high school, the gas laws, they are directly related. So in other words, if the temperature increases, the pressure also increases. And if the temperature decreases, the pressure decreases. An easy way of looking at it is, if we have a balloon, all right, and we blow air into that balloon, eventually that balloon becomes taut or hard, if you will, all right? The pressure inside the balloon is increasing, all right? But also the temperature, the air inside that balloon, the temperature is also increasing. It's getting a little warmer. So if we were able to measure that, it's a slight amount, but when we release that air from the balloon, as the pressure decreases, the temperature of the air inside will also decrease, will become cooler, slightly cooler. All right? So,
on the atmosphere, when we go high,
yes.
The pressure decreases.
Yes, and is it warmer or colder?
Colder.
It's colder, so you see? So the temperature also decreases. That's another way of looking at it from the natural system. Thank you there, that's a good example. At sea level, we have one atmosphere of pressure and we have X temperature, right? As we go up a mountain, why is there less pressure? Why is there less pressure?
The
Yes.
more close to the ground is less pressure.
Oh, yeah, there is less pressure, and it has to do with gravity, specifically why?
Space.
What is space?
Here, there's more pressure.
Yeah, what?
Here, we're more close to the
To
top.
what? To the top of what?
And then the atmosphere.
To the top of the atmosphere, the stratosphere, or whatever layer you want to consider. There is literally, there is what? There is less what on top of our heads? There is less air molecules. And those air molecules, even though they are in gas, they're also influenced by what? By gravity, because they have some mass. They have mass, all right? And so they're influenced by gravity. So gravity is pulling. That's what keeps the atmosphere in place. Otherwise, the atmosphere would fly out. We'd have no atmosphere, right? In fact, that's another phenomenon that happens in celestial bodies that have less atmosphere, less gravity. They have less atmosphere. Like the moon has practically no atmosphere because it has much smaller gravity. So that gravity is not sufficient to hold on to the molecules. The molecules fly out. Mm-hmm.
Can the celestial bodies lose gravity?
Can the celestial bodies lose gravity? The short answer is I don't know, because I'm not an astronomer, but thinking about it, the way to lose gravity would be to lose gravity or lose atmosphere.
Well, lose gravity.
Well, right, if they lose gravity, they lose atmosphere. I think at least, so you get opaque bodies and luminous bodies, right? Opaque bodies are the planets and the asteroids and moons. They reflect light, but they don't make their own light. And then the luminous bodies are essentially the stars. But even stars go through cycles. And eventually stars will collapse and burst. They lose their gravity then, okay? But now they have, while the solar system is going on, they have a gravitational field and pull, which is what's keeping everything in orbit. Which, by the way, there's an experiment now, it's a long-term experiment that they're trying to determine. They're trying to detect, actually, gravitational field through space. Because the thought is that gravitational field not only keeps each particular solar system in place, for example, it's keeping the Earth in place with regards to the sun and all the other planets in our solar system, right? But also galaxies and between galaxies. So these gravitational fields are influencing pretty much the whole universe one way or another. And that is inversely related to the distance to the origin, to the core. So that the further out from the core, the weaker that field is, but still there, all right? And then seemingly there are traces of the gravitational field of the original, all right, Big Bang, which all of the universe, the matter and the energy of the universe was concentrated in what is called singularity in single point. So imagine the gravity of that, right? So when that explosion, the Big Bang, supposedly there's background gravitational field from the origin of the Big Bang that is still out there, traces of it. So exciting. It's kind of a radar or some kind of a detection device that is thousands of miles with trying to do a triangulation between satellites.
Super wave or something, mega super wave.
Yes, yes. Anyway, those are very sophisticated experiments that are occurring with the technology that is at hand. So back to then the temperature and pressure, they are directly related, not inversely related, okay? So if one increases, the other one increases and vice versa. The last thing I want to mention, and all this is with the hydrosphere, or with the atmosphere lecture, is I neglected to mention air pollution as such, as one of the major contaminants, especially in urban areas. And air pollution has to do not only with gases that contaminate like CO2 and methane and so forth, but also particulate matter that is suspended. And particulate matter that is suspended is typically measured in parts per million, just like we saw parts per thousand of salinity, right, of minerals, the salt and water. The particulate matter in the atmosphere is measured as parts per million, and sometimes even parts per billion, depending on how much or little there is. But that particular matter, particulate matter, can be a major agent in respiratory diseases, typically asthma. Okay, so to give you one graphic example, in Central Florida, which is the area where there has been a lot of sugarcane growth and production, right? The typical way of getting rid of the old sugarcane after the harvest and all that is to burn the fields. And that produces a lot, in addition to the CO2, of course, that it pumps into the air, it produces a lot of just carbon dust flying around. Sometimes we can even smell it. Well, there are also wildfires that occur in the Everglades, but the burning of the sugarcane in Central Florida produces this particulate matter that floats around, and it's seasonal, which has to do with the growth of the sugarcane, and it can be traced a correlation between the seasonal outbursts of asthma attacks and asthma related illnesses, right, crisis, is correlated to the seasonal burning of the sugarcane in Central Florida. But as that cloud, say, expands to the coast where most of the population is, right, it affects the people away from Central Florida, including down here in South Florida. Part of it also has to do with the wind pattern and all that. But so particulate matter is a major contribution to pollution. And the word smog, all right, is kind of a composite because it's particulate matter that mixes in, especially with humid air, with fog, and you get smog, all right? And it happens typically around urban areas, which is where we have the highest concentration of people, high density, all right? Another one that was very graphic a few years ago, remember the Olympics in Beijing, China? Whenever there was a shot that was taken far away at a distance of the whole city or the stadium or whatever, there is this yellow, mustard yellow cloud on top of Beijing, right, that sits there. Some mega cities, some of these megalopolis in the world have another characteristic of, aside from their high density, is that they typically have a cloud of smog that sits on top of them and kind of moves around and swirls around, but doesn't totally ever leave that city. Mm-hmm. Regardless of Mexico City is another one. Part of it has to do with its in Santiago. Big problem. Yes. Smog. Yeah, with smog, yes. Right. It just sits there. I was in Santiago one time many years ago in the 80s, and it had not rained for 2 years. Exactly. Wow. Very dry, extremely dry, because the pattern of wind there comes from the east, above the Amazon basin precisely. So remember, the wind pattern from the oceans in is warm, humid air, right? Because it picks up humidity from the surface of the ocean through evaporation. And then it hits the land, it cools down, causing precipitation. But what happens is the mountain regions acts like a comb, like a humidity comb. So when that warm, humid air goes through the Amazon basin, which is fairly flat, close to sea level, it is dumping a lot of that rain. And then it hits the Andes, goes up, that warm, humid air, as it rises, it cools, right? Condenses, drops more rain. So the eastern slope of the eastern range of the Andes filter out the humidity. By the time that wind gets to the western side, where Chile is, it's dry wind, and Peru also. So that La Costa de Atacama, all that desert, the Desierto de Atacama, the whole Pacific coast in South America. In North America, we get the reverse effect. The winds coming from the Pacific are the warm, moist winds coming inland, right? And what range do they hit? The Rocky Mountains, the Rocky Mountain range. And so that filters out the humidity, which dumps down where? The three states, the three western states, California, Oregon, and Washington State. All that is very humid, lush. You have the California, the vineyards, and then you go up north, you have the Cascades and all that. Very beautiful, green, lush. But once that air goes above and condenses and precipitates on top of the Rockies, whatever humidity was left falls on the Rockies themselves with all the permanent snow, the white caps. Eventually, when it comes down on the eastern slope of the Rockies into the Midwest, dry air, and you have that whole desertic region in the Midwest that is very dry. Of course, it's also the breadbasket because it's being watered artificially, all right? With secondary, tertiary, or quaternary type of agriculture, definitely supplying artificial. But sometimes on the eastern side there in the Midwest, you have days and days just clear blue sky. Think of Arizona, New Mexico, Texas, no rain, no cloud in sight, very dry.
And non-star, we can see the stars now nowadays.
Yes, yeah.
My country, my town,
Mm-hmm.
is that we have a lot of stars.
Yes. Where is it in Venezuela? Is it in the mountains or?
No, I know in the mountains, well, close 3 hours from Caracas.
Okay.
Caracas
Is Ohio? Yes. Mm-hmm.
We are in the center.
The center of Venezuela.
Yes. They call La Puerta de los Llanos, but we are not
Okay.
really inside de los Llanos,
Okay.
but we belong to that.
So it's somewhat above sea level, but not high in the mountains.
Exactly.
Right. It's halfway, midway. Yeah.
But it's more Llanos, we like to say it's maybe Savannah.
Okay. All right.
We
Oh,
have a
okay.
lot of
Oh, yeah.
cows and
Yes.
all
Pasture,
the
grassland.
pastures for-
Mhm.
Yes.
Mm-hmm.
Ganado, cría de ganado.
Right.
y
Yeah. For cattle. Mm-hmm.
agriculture.
And you used to be able to see the stars
Yes.
at night.
Especially when you are in the farms. In the
Right. Out in the
savannas,
countryside. Yep.
and you can see the,
Right. Yeah.
the whole sky with the
Mhm.
stars.
Yeah. Part of the issue for not being able to see the stars in urban area is the reflection of light. It's what is called the albedo. The albedo is a diffuse light that is bouncing around. Even at night, there's a diffuse light just from city lights, okay, that bounces around the atmosphere. So that creates kind of a filter, a whitish, it's like putting a whitish filter in front of the eyes or whatever telescope one uses. So in the rural areas, you don't have that
It's
albedo
very
bouncing
dark.
around.
It's so dark, there's no light.
Exactly.
Just-
Exactly. Yeah. They say the best places to see the sky at night here, the stars here, is in the Everglades, in the middle of the Everglades.
Yeah.
But you got to take mosquito repellent because they can carry you away.
We have a society, it's a Southern Cross Society.
Yes.
That there is an astronomical society.
Oh, yes.
They have what they call star parties.
Oh, yes.
The thing is, you get there early because they do not allow you to go in there with your car. There's lights on.
Right.
So you
Exactly.
gotta be careful. It's kind of creepy
Mhm,
because
yeah.
you're out in the Everglades with
Exactly.
no lights and you don't know where you're going.
No.
Right, right,
Yeah.
yeah.
It's completely
Well, you
but
go in
I tell you,
groups.
You get out there, it's all beautiful.
It is. You can actually see the Milky Way
Yeah.
swath of band.
They have they take their telescopes. out there.
Telescopes, and they do
Stuff.
tracking. Sometimes they can, with computers, they can do
Very nice.
tracking. Yeah, exciting. Okay, so those issues that I wanted to polish up.
You mentioned parts per million and what else?
And sometimes part per billion if it's a trace amount, all right? But typically particulate matter that makes up air pollution is measured in parts per million. Okay? Sometimes, I really don't know if it's in parts per thousand, that would be high density. All right, so you notice that so far we've been talking about the lithosphere, the hydrosphere, the atmosphere, but I've been concentrating really on matter. But there's that other thing that is in the universe that is energy. I haven't talked about it too much. So today's lecture is devoted totally to energy, all right, to energy sources, consumption, and production of energy. Because we don't see it as much, but it's definitely there, and we are very dependent on it. And the more civilized we get, let's say, or the higher density and the higher sophistication of life, complexity of life, including all the technological gadgets, the more energy we require. Okay, so we are a species that is voracious for energy. No other species has the demands of energy that we have. Beyond the natural, that would be essentially just food to keep us alive. Beyond that. All right, so energy production and consumption, all different sources of energy, it can be classified into two main types from what is of interest today, whether they are renewable or not, whether the energy sources are renewable or not renewable, okay? So I'm going to start with the non-renewable sources. Non-renewable are the fossil fuels, which include coal, petroleum, natural gas. You notice the three states of matter are represented here. Essentially a very complex, thick, and high energy molecule or compound. These are three states of carbon compounds. And if we take it down to the molecular level, that high energy bond is what? The covalent, not the hydrogen, but the covalent bond between the carbon molecules. You notice what element is a common element between these three compounds: coal, petroleum, and natural gas. The one element, carbon, is the skeleton, is the core element. Carbon is the core element of coal, petroleum, and natural gas, okay? Now, specifically, the carbon to carbon, so they're carbon polymers, in other words, chains of carbon. And those bonds between the carbon atoms are known as covalent bonds. They're very high energy bonds. So when that high energy bond is broken, that energy is released. When it's released, depending on how it's trapped and channeled, it can be available for work, for doing work. All right, and that's what we call power or force. All right, so we can see that chemical energy as potential energy, right? Which can be transformed into kinetic energy, energy that is doing work. At the natural level, that's when we do exercise. We are burning glucose, we're burning those carbon bonds, right? And extracting the energy from there. So fossil fuels. So these are high energy compounds, very high energy compounds. The downside is that the typical way of extracting that energy is through burning. And what are the byproducts of burning is CO2, which is a greenhouse gas at natural temperature. All right. The other one that is not renewable is nuclear, even though now the new generators, the new generation of nuclear plants include the recycling of old rods. So from that perspective, some people are trying to make an argument that nuclear energy can be considered renewable in the sense that it's recycling the spent rods of old previous generation nuclear plants. Something very exciting that is happening in that area. Anyway, getting ahead of myself here a little bit. On the renewable, there's an increasing number of renewable energy sources, okay? Solar, wind, hydroelectric, geothermal, wood, biomass, and also biofuels. We'll look at each one of these in a little more detail and the percentage contribution in the United States to energy production. So that's just an overview. Let's go now into the non-renewables. First, the fossil fuels. Of course, we talked about coal, petroleum, and natural gas. So these are just some examples. This is what is known as strip mining, which of course takes down a mountain, literally, a mountain that you can see this particular mountain or hill has a lot of carbon in it. It's essentially a huge block of carbon. And so strip mining means literally taking that mountain down chunk by chunk because it's a mountain of coal. That's when it's above surface. Below surface also there are mines, coal mines, that tend to be very deep and wide and so forth. But just to say that coal is available either at the surface of the earth or toward the surface or even below the earth. But it's coal that is very rich in energy, especially for combustion. So there's a strip mining, and yes, it does destroy that mountain in the end, okay? So it's high impact on the environment from that perspective. If it's underground, we don't see it, but the mines are there. There are other dangers associated with mining underground, typically the pressure and also the cavities themselves can begin to collapse and so forth. So there are dangers everywhere in this industry. Now, what happens to the coal itself is piled up and is processed through factories, coal plants, to obtain the energy, okay? And there has to be an energy transformation here, an energy exchange from the chemical energy that we said is potential energy in the carbon molecule. Eventually that has to be translated into electric energy. So there's an energy transformation from chemical energy to electric energy, all right? Carola.
Excuse me, one question. When you talk about non-renewable resource,
Yes.
what does it mean really? Because when I see coal, petroleum, natural gas,
Exactly.
for me it's something like a natural. It should be like
Yes.
a renewable. When you say it's not renewable, so
Thank you for that question, yes. So, as I said, this mountain is being dismantled, is being taken down, all right? And that mountain will not be renewed, will not be replaced. So when we burn coal, we destroy the coal. We have no more, if I have a chunk of coal here and I burn it, I no longer have the coal. I have burnt it into CO2 and extract the energy of it, but that coal has not been renewed. It will take the earth millions of years to renew. Maybe it's a little easier with petroleum. Are you people okay with the light issue? Oh, it's a motion thing. Would you rather turn it off now that it went off? Would you rather have it off or on?
The light?
Yeah, do you see okay? You see better without the light?
I think turn off.
Yeah, Patrick is normally in charge of that. He's not here today. I think it's the first one. Okay. Is that too dark or is that okay? People, it's okay?
Yeah.
Because we have the windows provide enough to.
Yeah.
Okay, so people who are taking notes, is that sufficient?
Yes.
It is? Okay, good. All right, yeah, you can see the projection better. Let's look at it with petroleum. It's a little easier maybe with petroleum. With petroleum, we go into the ground, take out the petroleum, and we burn it, right? And we make electricity out of that. Once that petroleum is burnt, we don't put it back into the ground. There's nothing to be put back into the ground, all right? So when we extract petroleum, eventually those oil fields, those petroleum wells dry out because that energy was made, that petroleum was made millions of years ago by the pressure of crushing what? Crushing forest? Right, fossils. But basically its vegetation is rotten vegetation, right? Yes, right. But so it was made by nature, let's say, it was made by nature under pressure by forests that died and got sediments on top of them. and they rotted. So the petroleum is essentially rotted forests, all right? That happened millions of years ago. When we extract that petroleum today, we're not replacing that petroleum. It will take millions of years, again, for Earth to make more petroleum. And typically, we would need some kind of a cataclysmic event of entire huge amounts of forest dying in a relatively short period of time and then being buried by sediments and compressed to make that petroleum soup, to make that rotten soup, okay? Which in nature took millions of years. And we're not replacing that petroleum. So that's why it's not renewable.
So petroleum is rotten what?
Rotten forest. It's mostly, and by the way, it's mostly, people think of a dinosaur rotting, but it's mostly plant material, right? Because when you look at the pyramid, the biomass pyramid, the bulk of the biomass is at the bottom, at the first level, the first layer of the pyramid. Other layers are smaller and smaller. So you get more petroleum from the base layer, which is the vegetation, the producers, the forest.
A few years ago, in the University of North Carolina, they actually started using, they did an experiment of petroleum, or they actually used pressure, like basically they put on a pressure cooker
Yes.
on steroids. They were using pig droppings, and they were creating, with the pressures, creating crude oil.
Yes.
But it wasn't cost effective.
Exactly.
You know, now if we were to run out of oil, then
Yeah.
it may become cost effective, but probably we'll have something to substitute that.
Good point. So nature has made petroleum kind of passively, just recycling essentially a forest that died and rotted, and with pressure, in other words, gravity, which is there, gravity is there passively, pulling down on those sediments, made the petroleum over millions of years. But if we were to do the same today, the energy investment into that kind of machinery is much higher than the amount of energy that the return that we would get from making that machinery. However, there's another side story to this, right? Which the core, the skeleton of coal, like petroleum and natural gas, is carbon, right? And if we were to compress natural gas, we could eventually compress it into petroleum, let's say. And if we were to compress petroleum, we would be able to compress it into coal, just changing the state of matter from gas, liquid to solid. If we were to take out all the impurities in coal and were to continue to compress coal down to the crystal structure of carbon, what do we get? We get diamonds, exactly. Yes, we get diamonds. A woman's best friend. And it is a crystal. It's a crystal of carbon. It's a diamond, chemically speaking. But it would be much smaller, so it would take a huge amount of coal to compress into a diamond. I don't know how much coal, how many pounds or tons of coal is needed to make a carat of diamond, all right? But what I'm trying to say is that there are machines now that make synthetic diamonds, but they're tiny. They're tiny because they have to use a huge amount of coal to make a diamond, but they can make synthetic diamonds now under immense pressure, and it crystallizes. The structure is a very hard crystal. Anyway, so here's the plan. One thing I wanted to point out is when you see all these fumes coming out, you think that's carbon dioxide? No, what is this? You notice how, yes, exactly, it's water vapor. You see how tall these, tower, what is this called? Chimenea. Chimney, thank you. The chimneys are so tall because they're cooling chimneys, okay? They're trying to cool the water vapor. But when it reaches the top, even as high as they are, is still very hot. When that water vapor hits the atmosphere, it condenses into these clouds. But this is mostly water vapor. In other words, there are filters in here that we don't see. There are filters to filter out the CO2 because that is a greenhouse gas and it's illegal to pump it out, at least in the United States and many other countries of the world. The problem is whether that law is enforced or not. So there's always a human factor, okay?
What they're doing with the excess CO2, they re-inject it into the water, into the land.
Yes?
Like the dry wells.
Okay.
The dry wells are dry because the pressures of the mantle,
Yes.
of the crust, as you extract the oil, it basically closes up.
Mm.
But by what they're doing is now they're actually injecting the CO2 into those old wells.
Uh-huh.
And guess what's happening? It's allowing them to open again and get the deeper oils.
Get more out of it.
That
Yeah.
is kind of like the cutting edge.
The latest, huh?
Technology.
Right, right. Yeah, it's getting very creative, and I'll
Yeah.
let this part kind of
It's really interesting.
jumps to the end on creativity, because it's trying to reuse the materials that used to be waste can be turned now into something useful. Anyway, just to finish up on fossil fuels, petroleum, which can be either taken out on land or from the ocean or the bottom of the ocean, right? So this is an oil rig in the middle of the ocean somewhere. And then typically this is gases that come out with that petroleum through the hole. There are also gases mixed in there, and it's part of the refining process. So this is typically methane and other gases that burn. And you notice they're far away out there from the rig because this is fire and petroleum is highly flammable. So you want to keep that fire away. But it's here. Actually, this is also part of a pollution control in the sense that it's burning these organic gases that are flammable. Otherwise, those gases would be released into the atmosphere, contributing even more to greenhouse. But this burn does produce, and this little cloud here, that is CO2. All right, so this does produce an amount of CO2 directly into the atmosphere. It's still better, though, than the actual gases, the organic gases being released without burning. All right, so it's breaking those gases down at least to the CO2 level. There's a chat here. A minute, please. Let's see. What a waste of energy when they do that. Yeah, okay. I suppose that they try to trap as many of these organic gases as possible. But again, you have to think, we have to think in capitalistic terms. In other words, does it make economic sense to rescue when these gases eventually reach a market level that is cost effective to filter them out instead of burning them? I suppose they'll do that. All right. But right now it's not cost effective yet. So maybe when these gases, whatever they are, become more rare, or another line of production can be found to those gases that is rentable. How do you say that is cost effective? Then profitable, thank you. That is profitable, then they won't burn them, they'll recycle them that way, right? Or they'll sell it that way. Was that another question? Okay, great. So I think we have to think in economic terms. What is cost effective? Production, consumption, supply, demand. Those are the things that are moving the market, right? For better or for worse, I think, in my personal opinion, is the best system that we've found so far. It's not perfect. What do we need? We need a regulation to maintain it so that it's not just driven by the bottom line of a profit. There has to be regulations because it would be more profitable, example, if all of these gases were not filtered and just pumped out into the atmosphere. It would be more profitable. Filtering out those gases takes money, expense, but it's a regulation that is in place so that we protect the environment. So that's where government comes in the form of regulation. But you have to keep those regulations reasonable so that the market can still progress and move and develop and evolve. Otherwise, if the regulations are overwhelming, it will shut down the industry. And that's a paternalistic environment. A little sidetrack here, kind of getting ahead of myself, but coming from Cuba and seeing the drastic change, what happened in Cuba in the past 50, 60 years, is that communistic system, the government pretending to be the big brother of society, shut down essentially the incentive of the Cuban people, right? It stifles creativity, exactly. Okay, so we see the issues that are at play here. It's a balancing act for sure. At the end of the day, there's no substitute for conscience, right? There has to be a social conscience. There has to be a conscience of maturity, of responsibility, wisdom, and that's what makes the system work better. The third one is here. This is actually a plant of natural gas, which looks as sophisticated and complicated as a petroleum plant would look like. Excuse me. But this is natural gas, which again is a complex compound, and that the industry tries to separate and purify the different gases that can be used for combustion. At the end of the day, all this has to land in some kind of combustion. So let me go to the next slide here. It's just a diagram of a coal plant. So you're going to need two prime materials basically to run it. Just generally speaking, grossly speaking, you're going to need coal and you're going to need water. All right? Because at the end of the day, it's about steam. It's about generating steam. All right? In other words, boiling the water. So the coal is coming in and being burned. As the coal is burned, these boilers or furnaces heat up the water that is coming in from some source. Ultimately, it's going to be a natural source. That water is being turned into steam. Now steam, the gas laws, steam wants to expand. It goes into high pressure. And it's that high pressure specifically that is causing the motion, all right, of the turbines. As the turbines turn, you have an electrical issue of surfaces that are rubbing against each other. You have a rotor and a stator. You don't have to worry about those things, but essentially that's what makes up the generator. The generator has a rotating core. Excuse me. La gotita. Yes. I've been talking too much for my life. And the vocal cords are complaining. Let's see. So what's in the generator? In the generator, basically, there are two main parts. One is rotating at the core around, and the outside on the surface of that circle, of that cylinder, are other coils, and it picks up the electricity that is formed as the core is rotating. So there's an energy transformation here from heat, from the burning, from the chemical first, the chemical of the coal, the carbon chemical, the carbon bond, the covalent bond, is that energy is transferred into heat in the water, in the steam, and then that heat is transferred into motion, kinetic energy of motion, making the turbines turn, and then that turning motion finally is the one that generates electricity. That's why this is called a generator. So there's an energy transfer originally from chemical energy in the carbon bond through heat and steam and kinetic energy motion, eventually into electricity. And then the electricity can be pumped into a transformer, purified, and then pumped into the grid itself. So what this does at the energy level is a transfer of energy originally from potential energy, chemical energy stored in the carbon bond, to eventually electrical energy that is available for doing work. Oh, so the byproduct, again, the big nemesis here is the CO2 and the other gases that are produced by burning, but mostly CO2. Therefore, there are filters here in this chimney to filter out, to sequester that CO2 as much as possible. So CO2 will still be released because it will be exorbitantly expensive to filter out 100% of the CO2. Okay, so some CO2 still leaks through after several layers of filters. Then what to do with those filters that are saturated with CO2 and have been trapped, what to do with them, again, involves creativity to try to find out some kind of a market value for it, all right? Maybe turn it into graphene or who knows. But I'm saying now we have CO2 that is sunk into those filters, what to do with it.
Okay, I have a question.
Question, Gloria?
What is the role of the river that in the coal plant? Can you please give me some information? I see the river is in the back.
So that people can hear your question.
The river and the coal plant. What is the role of the river? You explained the stream, you know, the
oh yeah, the role of the river. Yes.
Yes.
Okay. Exactly. The role of the river. The river is providing the water, the liquid water that is needed to be heated up into steam, to be transformed into steam. Okay. Now, what we may not get a good sense out of this line is that this is very high volume, very high volume. Okay. Looks like these are mountains of coal, all right? Looks like we have mountains of coal that is being processed and burned. Then we need a very large volume of water also to be processed through here to generate this steam.
Okay, thank you, Father.
So instead of just having one turbine, this is just a diagram, you would have maybe dozens or hundreds of these turbines going on, and they would be huge actually. So there's a large volume of water that is needed, fresh water, okay, to generate this steam. But this is also being collected here. The steam eventually is condensed down back into liquid water and pumped back out into the river. So this would be upstream of the plant above the plant height, if you will. And then this is downstream, the return, you see? The return is downstream on the river. What could be said is that the temperature, the average temperature of the river upstream before it enters the plant is going to be a lower temperature, or this water running downstream coming out of the plant is going to be a warmer water downstream, all right? And again, I don't know the exact numbers, but changing the temperature of the river will also change the ecology of the river, right? Of course, because different plants and animals live at different temperatures on that river. So some plants and animals could die, but other plants and animals could live that do not live in the upstream. But it will change the ecology is what I'm saying. Therefore, to have a minimal impact on the ecology of the river and the surrounding area, because it's not just the river, it's the river banks, everything, and the atmosphere that that river is generating locally in that, or regionally, right? Because the river is also evaporating water and humidity, and it's influenced the entire region. Just kind of thinking out loud here, there would be regulations as to the allowable temperature of the effluent of the water coming out of the plant. That if it's very hot water, nothing's going to grow there. Or maybe bacteria, you get a bacteria bloom, you get an algae bloom, that is not good for the ecology, right? So there has to be, the factory has to invest money into cooling down part of that water. Part of that water can also be recirculated. You see here's a recirculation. Part of that water can be rescued and recirculated, and it will take less energy to heat up that water up to steam because it's already hot water, all right? But part of it is put back out into the river, so it's not 100% recirculation here. So fresh water is coming in. If fresh water is coming in, then some of that water has to come out also, otherwise the system would just explode with too much water. So this is just a diagram, but when you start looking at it in detail, there are more complex issues associated with this diagram, right? Part of it is cooling down this water so that it's acceptable temperature to be pumped back out into the system. Not to mention whatever impurities may have been picked up, either leakage from the gases or even as it goes through the system, whatever impurities may have been picked up there have to be cleaned out before it's pumped back into the river. So again, this is a simplistic diagram, but at least it shows the matter flow and the energy flow, all right? But you can see that it's not mixed because this coal is burnt up and this plant is not, it's consuming coal, but it's not making coal.
Father, can we say that the river can be a recycle as well? Since
I'm sorry, I cannot hear you too well. Is there a way that you could raise up your volume a little bit, your microphone?
yes, I will try. Now you hear me?
I have you at 100% over here.
I do that too. My question was, can we say that the river can be a recycle as well for the coal plant, since they have to go back again to help?
What is
the recycle? The river can be a recycle as well?
That the river recycle?
Yes.
Not really, because the water in the river is being recycled, but the water is affected as it goes through the plant. So it's not a very clean recycle. Plus, the river did not need to do that. This is being imposed on the river, if you will, all right?
Okay.
So yes, the water is recycled, but if we can find other ways of cooling that water or using that water further, for example, one side effect, at least up north, would be to use that hot water to channel it through a water system to warm up a city. To warm up either the sidewalks. I know, for example, when I was studying at Purdue, in the winter it snows quite a bit, and so they have tubes, piping that runs through the concrete on the sidewalks. It's an extensive, it's a large campus, and it has a lot of sidewalks, all right, connecting one building to another, and there are pipes that are hidden inside the concrete slab of the sidewalks, and in the wintertime, they run hot water through those pipes so that everything else has 1, 2, or 3 feet of snow, but the sidewalks are all clear. And it's an initial investment of putting those pipes into the sidewalk, but then it saves on, you don't have to maintain the sidewalks, you don't have to be cleaning them with machinery and personnel and the expensive personnel, right? And exactly, it will break up the concrete at some point. So it was an initial investment of building those sidewalks with the pipes inside, but now it pays off over the years because there's zero maintenance and they're clear. So bottom line, the university can also function in the middle of winter, even if there's 2, 3, or 4 feet of snow all around you. The students have no excuse for not going to class. And I say that it was snowed out or snowed in. And Purdue has, I think it's about 50,000 students, so that's significant. And a lot of bicycles. It's like, you think you're in China, you think all these bicycles, thousands and thousands of bicycles. So that's one creative way of taking this water out and using it for something. Okay?
Okay, thanks.
Sure. Okay, let's move further.
So coal is what the trains used to, the trains.
Yes.
Transportation.
Yes, there are some trains that still use coal, but less and less because that's just coal that is burnt out into the atmosphere, all right? Trains typically have gone now into diesel, which is more purified and doesn't put out as much CO2 as the old coal trains where you see manually putting in with a shovel. Exactly. Exactly. Yes. Yeah. All those engines have been replaced with diesel or even better, electric. Right? The tracks themselves, they run. There's 1/3 rail that is the high electric rail. And then the next generation, the newest generation of train is magnetic. I actually have that at the bottom slide. The last slide, the 20th slide on this series. Okay. Now this whole issue of energy is exciting and challenging, right? Next one, talk about challenges. Right. For some reason, yeah, okay. Fracking. Fracking is also in the news, it's controversial. So just very briefly, this is what fracking is. Part of what Tony was saying is trying to extract more gas or petroleum that is trapped very deep down into layers of rocks that are down here that are called shale, all right? And shale has coal, and it has petroleum, and it has natural gas all mixed in. If you think of a sponge that is just full of coal and petroleum and gas, natural gas. So it's like a sludge, right? But it's high energy. Bottom line, there's a lot of carbon bonds in there, covalent bonds. So, but it's not available because it's trapped into the sponge, into the shale rock. So it's not easily extractable. It's not like hitting a pool of petroleum that under pressure will naturally come out, right? And it's also typically very deep. We're talking about 2 to 3 kilometers down. The official name or the scientific name for fracking is hydraulic fracturing. So they're fracturing the rock with hydraulics, in other words, with water, with pumping a sludge, a brine, what is called a brine, which is a salty water. It's a mixture of salt and sand under high pressure, and that fluid is pumped down in there to get into those fractions and to widen those fractions and to get out, seep out whatever oil or gas is there, which will mix with the brine, all right, and then will be brought back up for processing. So that's, in a nutshell, the fracking is done under high pressure, and it's an attempt to seep out, to extract whatever organic compounds are trapped in the shale rock. As it does that, it displaces that shale rock, so it can cause tremors that transmit through, but it's very deep down, all right? So typically those tremors are filtered through and amortizado, they're cushioned through the layers of the crust, all right? And also it's much lower than the aquifers. Most of the aquifers that are used for drinking water or for irrigation are in the upper layer, okay, in the hundreds of feet, hundreds of meter deep. There are some deep aquifers down here, yes, which could be contaminated with the fracking, but they're way below the aquifers that are normally used, which you can see here typically are more abundant closer to the surface. And these are the aquifers that are normally used either for drinking water or for irrigation, which we need water that is not contaminated, of course, all right? So there can be some contamination of these deep aquifers down here. Also, blowouts can occur, which is a danger. And also seepage of, as these organic compounds are being extracted from the rock and released from the shale, some of them in gas form will filter through, will seep through, seeking to be released because they're gases, so they're looking to get out of the crust. And one major one is methane, So fracking can also release methane into the atmosphere, and that's why it's controversial. And of course, in this kind of setting, there's no way of filtering out this methane, right? There's no way of putting filters over an expansive area. We don't know exactly where the methane is going to come out. Mm-hmm. So it's controversial. It has its up and downs. We'll have to see economically at the end of the day what is cost effective. Another creative idea, I was talking to get into nuclear plants. Just keep in mind this is the typical design of fracking. They go down vertically, again, 2 to 3 kilometers, quite deep, and then they go horizontally, kind of in an L shape like this, okay? Keep in mind this shape because this is going to be important when we get to nuclear energy slide. So if we look at the picture of petroleum specifically, how it's being refined, that gook, what is being extracted from the petroleum that is usable for humans and for energy, most of it, almost half, is turned into gasoline, right? We can ask the question, what is petroleum turned into? At least in the United States, most of it is for gas, or half of it is for gasoline. And then another third is fuel for either diesel or jet fuel, right? So you can see the vast majority of it is for fuel, either for cars, trucks, planes, automobiles, okay? What is left is more, it's a thicker fraction, if you will, a thicker fraction of it, asphalt, for pavement. Heavy oils and lubricants are also a small percentage, globally under 10%, around 10%. And finally, the last 10%, 11%, the last fraction, what in these other products are more on the solid side, very especially plastics. So this is where we get the plastics of all different kinds of plastics. Plastic. So imagine how much energy and how much technology and how much industry it takes to make a bottle like this from petroleum.
That's a process. You use petroleum to process the plastic.
To make the plastic. This, yes, the polyethylene, right? This burns, right? So what is making this bottle, the plastic in this bottle, was inside oil, inside petroleum, inside that gook, the black gook of petroleum, right? That thick black gook. The molecules that make this bottle were in there. It made the cap also. It made everything. And the label, plastics, they come from there, right? So you can see that oil, petroleum, is a very thick and complex and rich molecule, if you will. That is a soup. Is like if you went into the refrigerator right now and pulled everything out from the refrigerator, put it through the blender and put it in a big pot, all right? Whatever is in there would be simplistic compared to what's in oil, what's in petroleum. Because the whole forest is inside the petroleum. The whole forest, all the organic compounds and inorganic compounds that were in the forest are condensed in this black soup. What I'm trying to say by this is that it's a shame, it's a crying shame to burn it because those polymers, those polyethylene and all the molecular structure that is in there is so rich that can be used in such a wide variety of things, right? Including building material, making car frames, I mean, you name it, the bumpers of the cars already come from plastic. Many parts of the car, the interior is mostly plastic. And other products, synthetic products that can be extracted from petroleum. So it's really a shame that we burn about 80% of it, and then we only use about 10% to making actual stuff, artificial stuff.
But the last time, I was not in the last video, maybe, I don't know if you talk about, I had a friend, she was telling me about, she was in a college and some teachers, I don't know what class she was taking, and they said they found a bacteria who eats petroleum?
Yes, yes, that was in one of the films last time.
I
Yes,
don't know.
right. Yes, and those are the creative ideas of recycling, right? Recycling.
But it's a natural bacteria.
Yes, yes, they're natural bacteria and they have been discovered and they do eat petroleum. They take their time, but they do it and they break it down into smaller compounds and even nutrients that can be recycled into the water, the salt water, that then becomes nutrient for algae or plants and back into the food chain, all right?
This is new bacteria?
Well, they've been around for a few decades. They've been discovered. I don't know exactly when, but they were discovered several decades ago. And now they're testing which bacteria are more efficient and so forth, and if they have other side effects, because part of that petroleum recycling could be producing, let's say, toxic gases or something like that. So you get rid of one problem and you generate another problem. So you have to be careful.
So this can be adaptation from bacteria?
Yeah.
According to the environment?
Yeah.
They start to.
Right. Well, the whole point is that petroleum is a high energy molecule. So why would nature waste it? Bacteria have already found a way of eating that. So in that sense, they're decomposers, right?
I always wondered the danger of bacteria then getting into the regular oil wells.
Yes,
Because
exactly.
nature's going to find a way. If it runs
Yes.
out of, say, the oil that's free in the
Right.
ocean,
Yes. Right. Maybe one thing that
it can mutate.
could prevent them from that is either the temperature or the pressure, right? Because they're used to the atmospheric pressure. So, but yes, exactly. And then that could be used in bioterror, and you start thinking all kinds of wild things.
Just think of the nuts we have now. I mean,
Yes. Yeah. So the layers of complexity are not going to get
any better.
You know, the cardinal was right. They try to live simple lives, but the layers of complexity keep increasing all around us.
You can't put the genie back in the bottle.
Right. Right. Did you?
This is also irreversible once you've generated these products, because burning plastic, for example, is highly carcinogenic. So that would be
Yes. That's the other.
harmful to them.
Exactly. That's the other part, is that some of these gases, once the molecules are extracted like this and are purified, then burning them produces carcinogenics that are not good. So how to purify that? Again, creativity has to kick in somehow. Another bacteria, right? All right. No, wrong way. Nuclear. Nuclear is still classified as non-renewable because it uses material, uranium or whatever material that is radioactive, and the radioactivity decays, and in that decay is the extraction of the energy. So it's atomic energy, it's nuclear energy, right? Remember when we talked about the strong bond between the atoms, or within the atoms? So in that sense, those atoms are being destroyed or decaying, so it's non-renewable. We're not putting radioactive material or uranium or rich uranium back into nature, right? That is decaying in a one-way direction. It's interesting, I just found this graph on the history of nuclear power, basically in the past half century, all right, how there was a rise in the 80s, and now it's kind of leveled off to the point that there are just under about 500 nuclear reactors throughout the world. But they have become increasingly controversial because of some major accidents in the United States. Remember the 3 Mile accident, 3 Mile Islands accident. And then in Russia, of course, Chernobyl. What is not listed here, I think it was in 2011 was Fukushima in Japan. And so that has given a bad press or bad perception to nuclear power. But in principle, nuclear power is extremely efficient in that enriched uranium can produce an immense amount of nuclear power, of electricity, to run entire cities from a single plant. And we have the case here, actually, in Miami, is Turkey Point, right? Turkey Point is a nuclear power plant that is south of us on the coast and is providing the bulk of the electricity of FPL for, at least for South Florida. I don't know elsewhere on the grid. But keep in mind that FPL is a state system, right? So I don't know how far north this plant, electricity is being taken.
The smoke is coming from this.
Right, again, so when you see this kind of smoke, right, these are cooling towers because it's going to come down one way or another to heating up water to steam, and the steam is what's going to move the turbines. It's just that you can generate an immense amount of heat with that nuclear decay, all right? But it basically comes down to steam. I mean, look at the proportion. Look at if you could, these are cars in here, right? These are cars and trucks. You can barely see these dots. This is a barge on the river. So you can imagine the size of these towers. That's what they can be seen from miles away. This is an entire parking lot here, all right? So you look at the proportion. I think this may be a truck, this little blue dot there, okay? But to your question, what is this smoke? Is this CO2? No. This is water vapor, okay? This is water vapor. These are cooling towers as the heat rises and it condenses on the walls. I'm sure there's a lot of dripping water inside these towers, but the rest comes out as vapor. But this is water vapor. So there are very strict regulations to try to prevent the CO2 or the radioactivity, for that matter, from escaping.
But in this case, they don't use anymore. They don't use coal. What kind of metal they use? Uranium?
So they use, right, they use radioactive material, which is uranium that has to be enriched and all that. And then that releases in the decay process, that releases an incredible amount of energy, all right, which is used to heat up water to make it steam, and the steam,
like the coal plant.
Eventually it's about turning turbines that generate electricity. So yes, at the end of the day, the core of the making of the electricity is the same, which is turbines by heat, all right, by steam under pressure. So steam under pressure. So what you're seeing here is the release of that high pressure steam that is very hot. And as it hits the atmosphere, of course, it condenses and cools and we can see the cloud. Now, what I wanted to point out is that these are early generators, early generations from the 70s, typically, when this was taking off, okay? In fact, Fukushima, the first reactors, which are the ones that were mostly affected, remember there was a tsunami, an earthquake that happened, and a huge wave hit it. They weren't predicting that. They did not put that into the calculation, but it was a catastrophic wave that hit that plant, which was on the shore because of the need for water, an immense amount of water. Anyway, those cores were built in the 70s. So even though it was still an existing plant, it was still functioning 40 years later, those early cores are from the early generation of nuclear plants, the ones I gave. So in other words, there were old cores that had kind of an old safety system. And what actually happened was that the tsunami shut down the cooling system, so it overheated. Those old cores did overheat, and that's why there was the breakdown. But the actual detail of the impact of the tsunami is that it broke the water pumps that keep the system cool. So really, it was not a nuclear disaster, it was a mechanical disaster because of the fail of pumps, of water pumps. Okay, and that's not nuclear, that's mechanical. So it was a mechanical failure that then caused the nuclear disaster. But the nuclear itself did not fail. In principle, there were systems that shut down the nuclear reaction, like it should have. It's just that there wasn't water, the thing went dry. It's like the car when the radiator stops, Okay, if the radiator has a leak, the motor has no problem. The motor is functioning fine, but it's not being cooled, so it overheats. That's a simple analogy. Anyway, what I was trying to say by that is that the new generation, which is now in the fourth iteration of nuclear plants, are much more efficient. They're hundreds of times more efficient than the old ones. They have safety mechanisms, learning from past experience. We've got to learn from our mistakes, right? They have such safety systems that the accidents that have happened in the past could not possibly happen with this new generation of nuclear plants because of the redundancy on the safety systems that they have, all right? When a problem starts at this point much earlier, what I'm trying to say is first, they're not going to build in a region that it could be a tsunami or an earthquake, something like that. But if there were something like that, it would shut down much earlier than the old plants did. So there's more safety systems embedded into these nuclear plants, precisely to make it cost effective, because there is such a high yield of that nuclear reaction, of that enriched reaction, that it's still worth putting in the money into all the safety systems that are needed to keep it going. I'll give you another drastic example, the nuclear submarines, all right? They can be down there for months and months. There's no other way to have that much energy to run an entire submarine than with this nuclear power. And the safety systems that they have, you never hear of a nuclear submarine blowing up, okay? Because they have put very sophisticated technology to make sure that there is no meltdown. Because, of course, the big thing with the meltdown is the contamination then of that nuclear radioactivity into the soil, into the surrounding area.
With Chernobyl, I think that the design was flawed from the beginning, and they knew it before they built it.
Right, so there we get into other layers. Again, the human factor. Notice where this happened. It happened not only in Russia, but it actually happened in the Soviet Union, right? This was kind of the height of the Cold War. So we know that there was a communistic regime there, and the state was self-regulating. Well, it was a fox keeping an eye on the hen house, right? So because of ideology, whatever, that system was allowed to be built without the necessary safety systems in it, and then they suffer the consequences to this day.
Right? When I did my master in public health,
yes,
my internship was in emergency preparedness. So I have an exercise with the Turkey Point happening
in Turkey Point, right?
Yes,
exactly.
Because it's the health department.
There you
so we had the human aspect, what affects first is the thyroid.
Yes, you're talking about radioactive contamination, specifically. Radioactive, yes,
In the
right.
Turkey Point, if something happens, a leaking or something.
Right. Yes, right.
So the state, the city is ready for any.
It is. There is an emergency plan.
Exactly. There is an emergency plan. And we did the exercise actually in what they call the center, first command, something like that.
Yes, the command center.
The
right.
command center.
Yes.
And all the agencies were there. It was
Yes.
very interesting. And
Yes.
everything was
Probably including FEMA and all the emergency agencies.
all the
right.
agencies around.
Yes.
Every water,
That's right. Electricity.
What can you imagine?
Yeah. What we call the infrastructure of urban living.
And there are 3 or 4 people who are the leaders.
Right.
That they say what's going on over
Right.
there.
Right.
And of course, they have the medication. I think it's potassium chloride to inject
Right.
the people.
Right. To absorb the radioactivity.
Exactly. And to prevent all the.
Right. That would be for direct contamination or direct exposure to nuclear activity, to radioactive activity.
And, it's so interesting because you see how one one person coordinate and all the agencies, for example, how many hospitals are we going to use?
Yes.
So there's some people have to go back to hospital in Jackson, whatever, so.
Exactly. The number of beds available, how far away they are on the map, on the grid, the distance from the event. Sure. Emergency coordination is a very exciting field. It's, again, complex. It's embedded with technology, right, to coordinate. And the technology also has to be independent. If the grid falls, they have to have their own backup systems and so forth to communicate, all the way up to satellite communication.
So in Doral, we have, they have a warehouse.
Right.
Full of, for anthrax attacks.
Wow, look at that. Okay.
Masks, gloves, all
The equipment, the high containment equipment that is needed.
For anthrax and for any nuclear.
Yeah.
What I see is, Father,
Mm-hmm.
this thing expire with time because
Mhm,
nothing happens,
right.
so they have to renew.
Yes.
A lot of
So the expense, yes, exactly. What to do with this? That's the price for civilization, right?
But, yeah,
Because it could be an accident like that, or it could be an attack. It could be bioterrorism. What do you do with it?
they were ready for any attack in, for example, Martin Stadium
Mhm.
in Kenya with
Oh, yes.
anthrax to any plane, airplanes,
Right.
helicopter, which
Mhm.
and I mean, that's very
Yes.
interesting.
It is. It's something that normally is opaque to us. We don't see it. We go about our daily living, shopping and working and sleeping and watching TV. But all this is the infrastructure of what makes urban living safe, right? Including drones for surveillance and things like that. Once they get at a certain height, you don't see it, but it's there. And they're photographing everything.
Yes.
Mhm.
But in the Second War, when
Yes.
there was, bombs, atomic bombs, I don't know how I see that accidentally that video. And they said there was a 4 missionary Germany. They were 8 blocks in a church, but they were not in the church. They was in a rectory. They
Mhm.
were praying the rosary, and the bombs come down and destroy everything. And they were still praying and didn't know what happened. When they come outside, they say they so destroy all the city, and the scientists, everybody went to there to see what's wrong with them, what happened with them. And they're still surviving now, and they say they never has been affected for the radiation.
So they were never affected by radiation?
No, the priest, they never affected the radiation.
What?
And
Are you saying the priest
the-
specifically?
they were
The priest?
The place were there,
Oh, yeah?
was not destroyed. The church was destroyed. The church, there was a church in the
Really?
place, the
Wow.
rectory. They were living there,
Oh, yeah?
and everything was destroyed. And they were like, the only thing they were always praying to give the rosary.
Wow.
You know?
Tremendous. This was in Europe, somewhere in Europe.
No, it was happening in the bomb atomics from Japan.
Oh, you're talking about Hiroshima and Nagasaki? Ah, okay. Oh, yeah.
And they say they don't have cancer. They still
Already?
living now.
Amazing.
They didn't
Yeah.
have any affection.
Sometimes you have some anecdotes like that.
Yeah, there was
They're mysteries, right?
Yes.
Amazing. Well, I believe in miracles, but
The bombs back then were not what we have now.
right, right. Yeah. Ed is saying here in one of the blogs, well, I think you can see, that there are 3, because Ed has worked with the power plants and is familiar with them, that there are 3 levels of redundancy on these, which apparently is adequate and sufficient, right? And Gloria is commenting that, yeah, you have to, right, so there's no substitute for the conscience, right? Gloria, if people want to do evil with their knowledge, then that's a chance. That's what we call open societies, take those risks. Mhm. Okay, let me move on to renewables. Yes, maybe it's a good time to break then. Okay, let me finish this slide, and because this is a transition, where we have, if we look at it in the past 300 years or so, since the building of the nation, the inception of the nation, the trend of the non-renewable resources, coal, petroleum, and gas, you see, have peaked at the beginning or the first half of the 1900s, first with petroleum, right at the turn of the century, and a little later with with coal first, right? And then petroleum, and then natural gas. But the general trends here, if you consider what we've been learning in statistics, in the recent years is a negative slope. All of these tend to have a negative slope, so their trend is down, all right? And the cumulative is also down, whereas nuclear is the dark blue. If you look at the inception forward, you see kind of an opening cone, all right? But nuclear, of course, is very controversial, so it's a question of perception in societies. It's anybody's guess whether this will increase or not. The scientists and a couple of nuclear scientists nuclear physicists that I've been talking to, they say that with that fourth generation of reactors, the transition from non-renewable to renewable, which is still generally very expensive, the transition is definitely nuclear, at least in the short term, short to middle term, in the next decades, until we become very efficient with renewable energies, all right? The transition that is cost effective is definitely nuclear, all right? So then we have to listen to those arguments of reason. No system is going to be 100%, of course, but for example, it's known that it's much more risky to drive a car than to go on a plane, because the safety systems on a plane are much higher than on a car, because the human factor, not everyone who drives a car is a professional pilot who has a lot of training and gets adequate sleep and all that is supervised, you know. So how we see car accidents, typically when I drive every day, I see at least one accident, if not 2 or 3 accidents, all right? And how often do you hear about a plane having an accident or falling? Not every day, for sure. Not 2 or 3 times a day. In the local region, when you take out all the accidents that happen in the US in an entire day, and then throughout the world, there are thousands of accidents, car accidents. And yet people have no problem driving around and getting into a car. But it's much more risky overall to be in a car than to be in a plane. And yet the perception is that it's much more risky to be in a plane. But it's a misperception because of the safety system.
I heard that they're using now actually carbon, like the equivalent of carbon ball, and the core of the carbon ball will be the uranium.
Okay.
And what they do is they put it in a basin, but it's a certain number of them.
Okay.
Will provide enough heat to create the steam. You don't have the mechanical rods going in and out. Because as you mentioned earlier, the more complicated something is, the greater the tendency for it to break down. And this is just basically a design that's think of the piles of the rocks on the bottom of one of those fish tanks.
Right.
They're there.
I see.
They do their thing.
Right.
And
there's less motion, less mechanics.
There's no mechanics. It's just very, very subtle. It's a controlled reaction.
Mm-hmm.
Everything is done before the construction.
I see.
So that when they construct it, it's there, and then I'm sure there's some sort of control, or they maybe lift some of those.
Right. Eventually, something has to move, right?
Yeah.
But the less mechanics there are,
it's not the rod going in and out of the tubes to create
the reaction is
the reaction.
Yeah.
And so I mean I think that's like one of the French design.
Really interesting.
And they're using actually the carbon.
Mm-hmm.
And they look basically like a cue ball.
Mm-hmm. There you go.
Very, very interesting stuff.
Yes, it's exciting. The technology is very exciting.
When I went to Ocala, I met a there. She was training horses, because she was a psychologist, a woman. And we were talking, and I was asking her what she's going to study, like for master. But I know psychology needs to be a doctor to be clinical. And she said, no, I'm going to do just only the master. And then, what is your specialization? And she said, I'm going to do that. I didn't know about that. Cars, Is it now actually the modern technology? The car has buttons, has more accidents than the other car, because for you pushing a button, you need more precise than when you move, like if you want to move the radio and you do these things.
Right.
When you want to do, you take more time doing the push buttons. They say now there are more accidents doing the things than doing that before, like other cars.
Right, interesting. In other words, it takes more concentration to work buttons than to work a dial, and therefore that's concentration that is taken away from the road into a particular detail. Interesting, yeah. So that human behavior, the study, and a lot of this thing is subconscious, right? It's subconscious, but it's real, and it can have an effect. Okay.
Yeah, so yes, I don't talk to get, but I realize now, anytime I'm in some place, they try to throw somebody to computer actions and new officers. Right. Somebody.
Yeah. These are the new creative interdisciplinary careers, right? That have to do with human factors, but also have to do with technology and nature, how to interact and how to connect those dots, and you can build a career out of that. Okay, let's break here, and I'll start with this slide coming back, because this will make the transition by percentages for us from non-renewable to renewable, all right? So the famous 5 minutes that turn into 10 minutes, yes, okay, very good, the human factor. So I'm gonna pause the recording now. Okay, hopefully this is recording again. Here's the audio, and this should be the video. Yes? So we go back to the second part. And what do we have? The transition between renewables and non-renewables. Looking at energy, sorry. That one? Okay. This is in the USA. About 90% is non-renewable, meaning that about the energy production, the electric production of the US is about 90% fossil fuel and nuclear, and then about 10% is renewable. In fact, if we go briefly back to that graph, that's the little dotted line that I put here. You can see it's about 90% the break between coal, petroleum, gas, and nuclear, right? And then the upper 10% is hydroelectric, and then the other renewables. So these two graphs match that way. We can read them that way. Now, with regards to the renewable, these are the main types, and it's by percentage of this 10%. If this is the 100% of renewables, right? This is 100% of renewables, and this is the breakdown. A quarter of it is hydropower, mostly dams. I'll talk about that. We'll talk about each one of these briefly. Another fifth is biofuels, which this was surprising to me, and also wood, just burning wood for industry. And approximately another 20% or 1/5 is wind. And the remaining 10%, more or less, is distributed between waste, recycling human waste, solar, which is very small because it's expensive so far, and then finally geothermal. With regards to this 90% here, the breakdown I've listed here is these are the gases that are produced by these non-renewable resources, the greenhouse gases. Most of it is carbon dioxide. Then there's some carbon dioxide also produced by forestry or land use. In other words, it's shown green because it's not burning biofuel. Then methane is 16% of the greenhouse gases approximately. Nitrous oxide is also a greenhouse gas, small percentage, but all these gases retain heat in the atmosphere, and so they cause that greenhouse effect, okay? And this is what renewables are trying to avoid, basically. Trying to avoid carbon dioxide, methane, and nitrous oxide, and then these are fluorocarbons, or fluor-based gases. How do we compare the US with the rest of the world? With regards to renewables, this is the consumption of renewable energy. Only this small fraction, only this 10% is actually 20%, is about 1/5 of the use of renewables in the whole world. So if we consider all of the countries of the world that are using renewable energy, that are using renewable resources for producing electricity, the United States represents about 20% of the global production of electricity by renewable energy. So another way of looking at this is that only with 10%, only this 10% of energy production in the US represents 20% of the renewable energy in the world.
So we are far away in the top.
Yes, yeah, we are very far away on the top of efficiency with regards to recycling, with regards to renewable energy. So imagine if we increase this renewable, which is the expectation, we could potentially provide even more percentage of the renewable energy of the world. And I mean, for an investor, this translates into money, right? Because we are essentially pumping we're pumping energy into the world market with renewable resources. That's how we can translate this in an economic sense. I mean, I'm not an economist by any stretch of the imagination, but that's my intuition, that it behooves us to increase this not only for our own sake in the United States, but because this is marketable, because it's renewable resources.
But to reduce the components of the, so if they want to, it has to be a burning, but when there is a burning, it's going to be a CO2. In a natural form, it's also going to be a burning. So,
yes, thank you. So there are two issues going on here. One issue is the burning, and the other issue is the burning being renewed? What is burned is being renewed or not, okay?
Yeah.
So that was a little bit of Gladia's point originally with regards to the river. Is the water in the river considered recyclable? In that aspect, yes, because the water is coming in and out and is being pumped back into the river, right? But there is burning in that process. Remember, it was not just water, it was coal. So maybe one way of looking at thinking a little bit more about her question, looking at that coal plant, the non-renewable part of the plant is the coal, but the renewable part of the plant is the water. But with a change in temperature, okay, which makes a big difference for the ecology.
For the decomposition of the, for example, so anything, any organic material,
yes,
has to be burned in order to.
Well, does it? That's the big question, because maybe with some other technology we don't have to. But even if there is burning, it doesn't necessarily mean that we have to pump the CO2 back out into the environment or release it into the environment. That's where the filtering system comes in.
There's always going to be some release of that.
There's going to be carbon dioxide. So carbon dioxide is a product of the burning reaction, yes, or the combustion. But it doesn't mean that we need to release that carbon dioxide product into the atmosphere. We have to capture it. If we can capture it and turn it into something, if we can sink it like the plants do, plants sink CO2, right? We saw that in photosynthesis. So we need, bottom line, we need processes that are analogous to photosynthesis so that we can sink that CO2 and trap it. For example, carbon is trapped into coal, right? So that's original CO2 that got trapped through photosynthesis into the forest, and that forest became coal. So that's trapped. Remember when we covered the carbon cycle? is the fossil fuels until and unless we burn them, that is sunk carbon, that is CO2 that is sunk, that is trapped, all right? So that's where creativity and technology, ingenuity, we have to continue along those lines. Aside from that is the renewable energies that do not burn, that can harness motion without burning, without using steam, without using another type of turbine, all right?
For that normal garbage.
Yes, we'll get there. Let's look at the normal garbage in a minute. Let's go there. Okay, so, but by categories, I'm just going from the percentage, the highest percentage down, all right? The highest percentage of renewable in the United States is hydropower, which is a quarter of the renewable energy production. And this is mostly dams, represas. It is
How do you call?
dam, D-A-M,
E.
A-M, una represa, all right? And sometime I heard at some point that most of the rivers in the United States, the vast majority of rivers in the United States are dammed at some point on the river, okay? Now, there are advantages and disadvantages. One advantage is that you generate a reservoir. And the reservoir is a larger body of water that can supply then water, instead of that water being, let's say, wasted downstream by the river, that water now, when it's contained in a reservoir, can be used for drinking, for irrigation, and also for recreation, because many of these reservoirs are large enough where people can go either put their boats in there, even sailboats or motorboats, or also picnicking and recreation, water sports around the shore, all right, including beaches in some cases. So there are definite advantages to dams, plus aside, of course, from the power that is generated through the motion of the water, which is essentially turning turbines. But this is an example where no CO2 is produced. And you have the same mechanism basically, but without burning, without steam, is the liquid water, the column of water as it flows down. So gravity is at work here in turning the turbine. But once you get to the level of the generator, basically it's the same thing. You have the rotor and the stator, and that's generating electricity, which can then be harnessed through a transformer and put into the grid. So that's why this is clean, because there's no CO2 production, because there's no burning, all right? Aside from that is renewable. Why? Well, because this follows the water cycle, right? In other words, the rivers are going to be the intermediate in the water cycle between rain and ocean. Remember the cycle? And because there is a water cycle, then it's renewable in that sense. So the main source of energy is what here? The water falling down because of gravity. All right, so renewable. Next is, this was a surprise to me, biofuel, actually, biofuel, all right? This involves another fifth of the energy production in the US. It's fairly recent, and the biggest biofuel by volume is ethanol, which is a type of alcohol, and it's in NOL. These are alcohols, and the typical plant is corn. And what of the corn? Well, part of the husk, but more than the husk is the actual grain and the oil in the grain. So this is essentially corn oil. Mostly by volume, it's mostly corn oil.
Right?
Yeah, canola is, or granola, or whatever the brand is. But so this machine is called a combine, right? A combine, which is a very large machine that goes through the field. And at the front end of the machine is picking up the crop. And then on the side, on the back side of here is the cabin of the person driving it. And on the back side is like a mini factory that processes that corn plant and is able to grind it down. Essentially, it's a huge grinder that goes then into this truck, and the truck is taken to the factory. And what do we have here is a combination of all kinds of the plant material has been chewed down, made into this mulch, all right? But it's very high content in the oil, in the corn grain, el grano de maíz. It's not separated from the rest of the plant material, but it's a very high content by volume of corn grain, of the grain of corn.
Okay.
All right? So that's why it's represented in yellow. It goes through a couple of processes. This you see are basically two rotors that squeeze or starting to squeeze, and the idea is to start extracting the oil or squeezing the oil out of the grain, right? And this continues the process with these helices that rotate. They're like huge grinders. Like this is essentially like a osterizer, a licuadora. All right, like a blender. It is mashing. It is different levels. This does the first level of grinding, if you will, to turn it into this pulp. This pulp then has high content of the grain, but it's still mixed in there with everything else. No problem. That continues to be grounded down through several more processes. Eventually, goes into a chamber where fermentation occurs. In other words, that oil has to be fermented into producing the alcohol. And that's what produces that. So this is a huge still, right? It's a fermentation chamber. And eventually this has to be fractioned out to fraction out the alcohol, right? The alcohol content. And the rest also, what is going to come out of here is bagazo, just the dried out vegetable part of, which is mostly cellulose fiber. That can be used, that can be dried out and compacted and used for fiberboard, which is used in construction and construction material, fiberboard, right? Maybe this is made out of fiberboard, a lot of material is made out of fiberboard. And the rest, the alcohol, has to go through a distillation process, a purification process, and eventually that is stored as ethanol, which is combustible, it's flammable, all right? And this also needs water for the cooling process. But this is a simplified version of how biofuel is obtained, originally from the crop of high yield with tertiary or quaternary agriculture that we have today. Remember that 4-time production of food for the whole world? Well, what's happening here is that now farmers, for example, in the Midwest of the United States, which is called the breadbasket of the US, right? All the granaries are there, most of them. They get a better price for their corn with biofuel than they get for feeding people in the supermarket or even feeding cattle, all right? Because this is also used for feeding cattle. Ethanol is a type of alcohol, which is a type of biofuel. It's a fuel because it can be burned, and it's bio because it comes from nature.
But it's using like alcohol?
It's a type of alcohol, but it's used in fuel, in gasoline. Do you see the label when you fill your tank? It says 10%, at least 5%, at least 10% ethanol. Well, this is the ethanol. This machine is the one that did it.
Mixing of
The gasoline with the ethanol, yeah. So proportionally, you have 10% less gasoline. So proportionally, you have 10% less CO2 produced and so on.
The bagazo that's used, is that used for anything?
The what?
The bagazo, is it used for?
Yes, that's what I'm saying. That's compressed into fiberboard. And there's a lot of material, construction material, walls, and also desks. And when you buy a furniture at IKEA, it's a cover, right? But the inside is fiberboard. It's not actual wood, it's wood material. It's fiber material. That fiberboard, that bagazo can also be burned and run a steam engine out of it, all right? Or it can be put into the waste cycle, which is another one that I'm going to show in a minute.
why they add ethanol to the test?
Because the fraction of ethanol is renewable. This is a renewable resource. Why is it renewable? Okay, so let's say you have gasoline, 1 gallon of gasoline, right? You put 1 gallon of gas into your car. If it has 10% ethanol, what percentage gasoline? 90%, right? And 10%, so 9-to-1 ratio, 9-to-1 ratio. Okay, so in proportion, you have diminished the amount of gasoline that you're using. You're not using 100% gasoline, you're only using 90%. Now, gasoline, is it renewable or non-renewable? Not renewable, but the ethanol is renewable. So a fraction of that gallon comes from a renewable source. Why is ethanol renewable? Why is this a renewable resource? Because it comes from a plant that can be grown season after season. So this machine, this combine, cut down this cornfield this summer. But next summer, this same field grew again with more corn. And it was planted and grew again. Every year, there was a plantation of corn. There was a crop. Every year, there was a crop. And so that's a renewable resource, right? With the fossil oil, with fossil fuel, if I pour gasoline on the floor, that's not going to give me more gasoline. But if I put a corn seed on the soil, it's going to give me a new plant. It's going to give me many more corns than just the one seed. I only need one seed to grow a plant, right? But the plant may have hundreds of thousands of seeds. So the yield has been 100-to-1, 1,000-to-1. That's renewable.
So that gasoline is compatible with the ethanol?
Yes, yes,
So
because, yeah, they're soluble to each other, right? That's another thing that I forgot to mention. You just reminded me when we talked about the water cycle, that water is called the universal solvent. Why is water called the universal solvent? Most materials dissolve, not suspended, but dissolve in water, all right? Precisely because of the polarity of water. So it's really the almost universal solvent. And whatever doesn't dissolve, we're talking about liquids. Whatever liquid doesn't dissolve in water is not water soluble. Typically, it dissolves in alcohol or oil, but oil, for example, dissolves in alcohol. And then alcohol dissolves in water. So that's another way of getting alcohol into water, for example, through alcohol.
But the ethanol is not why we can't replace the
100%? Okay. I'm not sure exactly why, but I think it has to do with the combustion. It's actually too efficient. It would make that motor blast, the combustion would be too high because it's too high in
That's correct, Father.
Sorry?
That's correct. The temperature would be too high, and the pressure limit on the engine would blow that thing to all conditions.
Right. Yes. Ed is confirming. He knows also about mechanics, and the combustion of ethanol is much higher than the gasoline. So actually, the impurity in gasoline keeps that combustion lower. But the alcohol would be much greater. But at some point, the question is, why not make a motor that is more efficient, that uses less amount of oil and is more efficient that way? Well, that's creativity. Maybe we go there someday, right, with technology.
That would be tied to a diesel engine, Father.
Oh, diesel, Ed, you're saying that, so diesel is what does that?
Diesel is the alternative. That's how the people are able to actually convert diesel engines into waste oil from restaurants, and they can burn the actual oil. Of course, your car starts smelling like cooked chicken, but it works.
Okay, Ed is saying, I'm sorry, it's through the speaker. Ed is saying that a diesel engine can be actually converted to use oil from a restaurant, waste oil from a restaurant and burn it. It's not very efficient and it probably produces a lot of residue, but oil can be recycled that way directly through a diesel engine. There has to be some adaptation of the engine. Anyway, let me move forward, please, into the other percentage. Again, another fifth approximately of the energy production in the US from the renewable fraction comes from wood biomass. We call this wood chips, all right? Just ground up wood. which can also be from forests that are grown specifically for that. Wood chips that are put through a furnace situation. And again, this typically will involve burning that wood chip to generate the heat, to generate the steam, to run the generator, to generate the electricity. So this is back to burning the wood, but at least this one is renewable in the sense that it comes from trees that can be grown. As opposed to the coal, which we're not replacing. All right, but what struck me is that it's a significant percentage, is 1/5 of the renewable energy in the US comes just from wood chip. It also tells me that there are vast plantations of trees that are being used for maintaining this industry, all right? Okay, we get into smaller percentages, just under another 1/5 is wind power. This one has the advantage that it is clean. In other words, there's no burning involved. So this one is green in that sense. Is these huge windmills. You can see the scale of these structures. These are trucks down here, cars, all right? So look at the scale, the size of these. These are the two main varieties. These are also huge. That's a house there, for example, down there, okay? Like a shed, more or less, the size of a human. So these are huge structures, and these are the two main designs, one with a helicopter type, and the other one, this one, also turns, but these blades, you cannot tell very well from this photograph, but these are angled a little bit. They're like that, angled a little bit so that they rotate in one direction and they spin around, right? So both are generating electricity. So there will be a generator in here, and down here, there's an electrical generator, again, generating electricity, but it's clean because there's no burning involved.
They're also experimenting with nano windmills. They'll place a sheath of this material that has the engineered windmill.
Right.
So the microcurrents are actually...
Yes, you were mentioning that last time, exactly, which at the nano level, we'll not see it with a plain sight, but it's there. Okay, it's there down microscopically, and all those little nano motors would have to be connected and electricity collected into a circuit, just like, well, that's miniaturizing circuits, just like they did with computers. I don't know if you remember earlier the circuits of a board that keep getting smaller and smaller, miniaturized down to the molecular level. So that's the creativity of the technology. Okay, so the percentages are interesting. Now we get into this. Oh, this one. So now we go into the last 10% of renewable energy, which is subdivided into biomass waste, literally the garbage dump being burned in a controlled burning situation. The other 5% is going to be solar finally, okay, and then 2% from geothermal. So let's look at this process briefly. Here goes our garbage into the garbage heap, and then this tractor picks it up and puts it into this bunker. Now this is inside the actual factory of garbage, right, of biomass waste, if you want to give it a scientific name. Just like the garbage collector is the sanitary engineer. Okay, so here comes the truck with garbage, which is pulled up and set down this chute here. And as it goes down, it starts breaking up into segments. And also this is a source of air because the combustion is going to need air for it to occur, right? And it would be too dangerous to burn it right here. So there's this retaining wall to separate, but you can imagine that this is a very hot process going on here. All right. So as the garbage is burned, as this is being burned in this chamber is going to produce, on the one part, ash, which is going to start falling down into this conveyor belt here. And it's going to produce a tremendous amount of heat from the burning, which will heat up steam, will produce steam. What is missing here is some kind of a coil or some kind of water source to make it steam. Or maybe the garbage has enough humidity in it to produce the steam. I don't know, but somehow there has to be water supplied here to generate the steam, all right? So there's maybe a step missing somewhere here. The steam then will drive that turbine generator, again, to generate the electricity that will be put into the grid. This is an actual number because this, I think, came from Maine or something like that, one of the states, so they put an actual number in it. But anyway, there's, the turbine, the generator is the one that's producing the electricity that is pumped into the grid. There are also gases, other gases that come out of here. Of course, this steam has to come out somehow. And these gases are going to have some toxicity in it. And of course, carbon dioxide, but also these other oxides. It's going to have nitrogen oxide and mercury and other toxic chemicals that have to be filtered out. So here go the filtering systems in this column. Typically, when you see a vertical column like this, it's filtering and also separating, fractionating. So this column is not empty on the inside. It will have different types of filters that will filter out different chemicals as it goes up and down the column. Eventually ends up in this chamber here, where there is more collection of particulate matter. And what is done with that particular matter, I don't know specifically, but depending on what it is, the product of burning, we can assume that it's going to be high in carbon content. How to use that, again, the creativity. The ash can now go to a landfill, but now what we have basically is ash, right, which is burnt wood or burnt material. And that can then percolate into the soil with rain and become part of the carbon cycle, but ash can then be sunk essentially. That carbon can be sunk into the ground, all right? I can tell you about ash, for example, that in the natural setting, pine trees, conifers in particular, because they are slow growing, in their initial states of growth, they cannot compete with weeds and bushes that grow very fast, and even grasses outgrow them, all right? And so there are, the pine trees in their initial stage are at a disadvantage, little seedlings, with regards to the other vegetation that is there. Over long periods of time, pines have managed to survive wildfires, fires in the forest. And what wildfires do is, at the same time, it clears the underbrush of the forest, turns it into ash. This is at the natural level. At the same time, it generates a heat inside the forest, and as that heat rises, then the cones, which contain the pine seeds, open up. So there are a number of pines that will not open, the cones will not open and will not release the seeds until they have reached a certain temperature that is much higher. It could be maybe 200 degrees centigrade or 150 degrees, maybe not centigrade, but anyway, it's much higher than the natural temperature. I mean, high in centigrades would be 40 degrees, 45 degrees is extremely high temperature naturally, right? We're not gonna get higher just from the sun heat. But these seeds will not open, the cones will not open up until it reaches an extremely high temperature in the natural setting. And then the seeds will be released. There's one pine in particular that does that. It's the ponderosa pine. It has that characteristic, but several other pine trees have that. Then what happens? The seed then will fall on top of that ash, which is called potash when it's mixed with the soil. And that actually makes the soil acidic, which is favorable for the pine seedling and not favorable for the grasses and the bushes that will tend to compete. So several things happen simultaneously with a wildfire. It clears the land for the pine seedlings to grow slowly without the competition of the weeds. It also turns the soil acidic because of the potash that mixes in, which is the favorable pH condition for the pine seedling to germinate. At the same time, it provides the heat for the cones to open up, right? And it's a whole cycle that these pines have adapted to that particular setting. So the bottom line of that is that wildfires are good for nature when they're wild, which typically will be on a dry season, a lightning strike, okay? Man-made fires is a different story because they are in addition to the wildfires. It is like that 4 gigatons of CO2 is in addition to the natural CO2 that's circulating already. So that's the danger there. And also because they tend to occur, man-made wildfires tend to occur near urban areas, which is very dangerous, right? But anyway, just made me think that this potash is not necessarily bad for the environment. It could create an environment that is favorable for certain plants to grow in forest. Okay, moving forward. Finally, we get to solar, which has all the hype and the excitement, but it's still fairly expensive because it's highly technological. The two main types of transforming solar or light into electricity directly, right? Making that without going through a turbine, without going through steam and all that, is either photovoltaic cells, also known as just photocells, which are sensitive to light, and then there's an electric reaction there that makes the transformation from light into electricity. And then each photocell has a little wire, and they're all connected, all those wires, into a main cable that will gather the electricity that's being produced by each individual photocell. So you see the checkerboard pattern here. Each little square is a photocell, and this is a panel. And then all these panels are linked together into an array. And so drop by drop of electricity, if you will, you produce a huge amount of electricity that way. And that's how it's collected. Some people have gotten creative, and this roof, this tile roof, when you start looking at it closely, they're actually solar panels that have been made in the shape of tile roof or a tile, all right? But it's actually a solar panel. So it's aesthetically pleasing instead of having that blue thing on top of your ceiling there, on top of your roof. This one is different. What you see here, these arrays, these are not photocells. These are mirrors. These are mirrors. And that's why they are in a circular fashion, because they are reflecting the light of the sun to this tower here. And this tower, which typically is some kind of a metal alloy, gets beyond red hot, it gets white hot, which is extremely hot. Remember, white hot is the core of the surface of the earth, right? Iron at the surface, that solid iron is white hot, and it's solid. Okay, so to get a scale of this, for example, this down here, this little white thing is probably a truck, all right? This may be a truck or a car. Just to get an example, these, for example, these here are cars and trucks parked in front of this building, which could be maybe 4 or 5 stories high. Just to get a size, a scale of how big this is. It's a huge tower that is way up here because the radiation of heat from there is intense. And all these mirrors are lined up so that when the ray, for example, right now, the bulk of the rays of the sun are hitting over here. And they're reflecting the sunlight onto this metal and it is heating it to this huge temperature. And all these mirrors are aligned in a funny way. You see this funny pattern of alignment, so that as the sun moves along the orbit from across the sky, some mirrors are being hit all the time and reflecting the sun there, the light. Okay? It's some kind of a metal alloy that can resist that heat, and then that heat is transferred down into this factory here. The heat is transferred down, and that heat is used directly to heat up water, to make the steam, to run the generator, but there's no burning. Okay, it's directly obtaining heat without burning. And so that way it's clean, there's no CO2 emission. So, but you need a relatively large spans of field for now. And I think I've heard that FPL is experimenting with something like this in the middle of the state and so forth, but you need an area that is away from urban. So that's solar, but you see it's highly technological, and that's why so far it's not a large percentage of the energy production because of the high technology involved in the investments. Finally, we come to geothermal, which right now is only 2%, but potentially there is an extremely large amount of heat that is there, accessible. We're talking about the heat from the core that diffuses out through the mantle of the Earth. That heat eventually dissipates out into space, increasing what we talked about earlier, entropy. It's heat that is dissipated and lost into space. Well, if we can trap some of that heat through natural vents, for example, here is just a natural vent reservoir. You can see this water down here is so hot, it's boiling hot, all right? You get this with geysers and natural water coming out from the earth, springs. Typically, springs are hot springs, to try to harness some of that heat, and especially when it turns into steam, then use that steam to turn the turbine that will turn the generator, move the generator to generate electricity, pumped into the grid. And there also has to be some kind of a cooling system so that the water will eventually return back to the soil, into the crust. But this is the essential part, is harnessing this heat, all right? Harnessing this heat without having to burn, and running the turbine in a clean way without a CO2 emission. Exactly. So the steam that you see here moving out, being emitted from these chimneys, that is precisely steam, and it's not CO2, it's clean. Plus, this water, keep in mind that this water may have some natural gases in it, typically sulfur, sulfides, that's why it smells like rotten egg, which we don't want to be pumping sulfur or hydrogen sulfide when it mixes with the atmosphere, because that is toxic. So there could be some filters involved in here, but typically it's not for CO2, it's for other gases that may come out through the mantle. Okay, so that's the last source of renewable energy. Moving forward in the next couple of minutes, just to see a trend in the past half a century approximately, from the 1950s forward, which is when the renewables started. You can see here, all right? All of these lines are close to zero at the origin. Coal is still the one that is producing most. This is the US. Coal is the one that's producing most of the electricity in the US still today. Also because it has been discovered that the US continent or territory has one of the largest deposits of coal and natural gas buried, in its soil, within its boundaries, within its frontiers. So certainly the economy is not going to waste that, right? There's environmental consideration, but again, the economy is what it is. And if that's a cheap source of energy, we have a highly industrialized society that is hungry for trillions of kilowatt hours to maintain the industry going and the commerce and down to the residential level. So that's still the main source, but there's a downslope here since the third millennium, all right? Whereas the others have generally an upslope. What's encouraging is looking at fossil fuels down here, specifically, petroleum, all right? Whereas, well, nuclear power, as we saw earlier, has kind of stabilized. It's horizontal now. It's anybody's guess which way it's going to go. A lot of this, in my opinion, is going to be PR. All right. The red is nuclear. Yeah. So that's horizontal right now, but the future, who knows?
And regulations, because it takes about 25 years.
Does it really? Right now, the
What they were saying.
the turnover rate is okay. Okay. Now renewables, I'm just looking at recent trends, okay, in the recent past, we see an upward tick here. If this continues, that's very encouraging because the green is the renewable overall. All of these together, that 10%, right? The 9.9% is represented here. So if this starts ticking up, that's exciting. How can we make that happen? These are some examples of creativity trying to harness on the production side and on the consumption side renewables. This is a wave worm, for lack of a better term. It's a long cylinder that moves back and forth with a wave motion. And again, whenever there's motion, you try to trap that motion into turning some gears to generate electricity, right? So this is just passive wave motion coming in and out, moving this creature to generate electricity inside. Another one is these floaters that go up and down as the wave hits the shore. And again, the motion is going to be transferred here where there'll be some kind of generator that is clean. There's no burning involved. On the consumption side, of course, electric cars are environmentally clean. Also, magnetic trains. You can see there's a void down here, right, between the train and the track. These are magnetic trains that are actually floating, being held up by magnets at a close distance are extremely strong. The repulsion of magnets at a close distance are very strong. The important thing is that it has to be a very flat surface, very flat on both sides, on the track and on the underside, on the undercarriage. If you have a bump, that's going to break up the magnetic field and it could make the train collapse and stick or something. But what's the big advantage of using magnetism for transportation?
That's a fast.
This is exactly, why is it fast? No friction, exactly, no friction. And therefore no heat production and so forth. And therefore it can move faster, typically in the hundreds of miles per hour, right? So much faster getting from city to city. Also, light. This is the standard incandescent light, the light bulb that we knew decades ago, which produces light by turning the filament white hot. So it's producing a lot of heat. Then the air conditioning has to turn that heat down and use more air conditioning because all these light bulbs are heating up the room, right? We're at the residential level here and even commercial. But turning that incandescent bulb white hot takes a lot of energy, comparatively a lot of energy. The standard was 60 watts back then. By using the lumens is the amount of light that is produced, which is approximately equivalent here, right? Certainly 800 lumens is as efficient for us to see. We wouldn't notice the difference in this room between 800 and 840 lumens, all right? So it's essentially for us the same amount of light, more or less. But look at the efficiency. This is the fluorescent bulb. In other words, what's inside here is not a metal filament, is gas. And the gas illuminates, the gas becomes fluorescent, that emits light. So that's a step down, only requires less than 1/3 of the watts to produce essentially the same amount of light, okay? But now the latest is this LED, which is called, exactly, there. It's called a light emitting diode. That's when you see LED, all right? And it's just a different physics and chemistry happening. The diodes, first of all, we'll have a diode in our pocket. If you have a cell phone with a light, that's an LED there. It doesn't get hot. It transmits a lot of light with very little energy from the battery of the cell phone, but that's an LED right there, okay? Highly efficient, right?
Yeah.
Highly efficient compared to those, and it only uses 1/6 the amount of the original fluorescent bulb. Mm-hmm.
And they do generate a lot of light.
Yes. Oh, yeah. It's very intense.
Refrigerator, like we just got a new refrigerator.
Yeah.
And the old refrigerator had a big bulb.
Mm-hmm. Right.
These now they have the panel on the side, and it's like you're opening up a spaceship.
Exactly.
Because it's like
let there be light.
yeah.
Exactly.
Yeah, it's incredible.
Yeah.
Incredible.
Exactly.
And even the freezer now.
It is in the night. If somebody else is
Yeah.
coming out.
Yeah.
Yeah, exactly.
Yeah, it's like,
If the whole house illuminates, you know, someone's getting into the fridge.
What's that old movie? Encounter the Third Kind?
Oh, yes.
Where the
Yes,
people
Close
walking
Encounter of
around
the
with,
Third
like,
Kind.
super bright.
Exactly.
Yeah.
Super bright, the white tunnel, right?
Yeah.
Exactly. There it is. The LED. Okay. God's manifestation is an LED. Right. But this, you can buy them now at, for example, Home Depot, just to mention a store. It comes in strips, and you can put the strip around and get rid of all the other stuff, all the other bulbs. Okay, very, very efficiency, of course, because they give you more for the bang. They're also going to charge you more.
And the
Okay.
light is like,
But look at the life expectancy from less than a year to over 20 years. Exactly.
what?
Yeah.
So it's $12 divided by 22 years.
Exactly.
And how many times do you do the light bulb?
Exactly. So you'll be there, you sold the house, and you're into the third house already, and your LED is still over there. Okay, so that's the efficiency that they're getting. It's exciting, creativity. This little film, I think Patrick had mentioned it. I think it was Patrick. Let me see if I can get this. How do I get this started?
It's kind of cool, those floaters.
I didn't do it.
Those floaters are kind of
Control,
cool,
control, control.
Click inside over the link.
Yeah.
Click.
Uh-huh.
And it will open another.
Yeah.
link.
Except, okay, and now enter, left click. Yes.
Did it work?
It's
I
a-
don't know, let's try again. All right, so here's the cursor. Control, left click.
Copy paste.
Yeah.
If everything else fails, then we do the right click.
Yeah.
Oh.
If you hit escape, Father, I think that
Yeah. This is the old way. Okay, internet. Well, this is just a couple minutes video here of using the plants for electricity, for generating electricity. But this one in particular showed a little bit of the technique of why. Where's that electricity coming from? Oh, give me a minute, stop, because I need to work on the sound. Turn this off. I feel like one of those one-man band has to work everything at the same
isn't
time.
that like
Let
one
me
of
see.
those initial experiments you get in science for the potato?
Yes, right. But this is more sophisticated because they've gone beyond the potato, which is the point that someone else was making is the potato is not renewable. The potato is going to die there.
Yeah, right.
Okay, but this one is actual living plants that are going on.
Yeah, Father also mentioned.
Plants like these could soon provide our electricity. In a small way, they already are in research laboratories and greenhouses at Project Plant E, a university and commercially sponsored research group at Wageningen University in the Netherlands. It's called the plant microbial fuel cell and can generate electricity from the natural interaction between plant roots and soil bacteria. It works by taking advantage of the up to 70% of organic material produced via photosynthesis that can't be used by the plant and is excreted through the roots. As naturally occurring bacteria around the roots break down this organic residue, electrons are released as a waste product. An electrode absorbs them and generates electricity.
Zonnepanelen maken meer elektriciteit op een...
Electrode absorbs them and generates electricity.
Zonnepanelen...
And is excreted through the roots. As naturally occurring bacteria around the root.
There. All right. So this is a crucial part. The bacteria around the root in the soil absorb that organic material that is excreted by the plants, that is not used, the excess glucose and other organic material. And as the bacteria are processing that organic material, naturally, around the roots, they are releasing electrodes, they're releasing electrons. And as they release electrons, they generate a current. They generate a current inside the soil. By placing a membrane through that current, then some of that current can be trapped in the membrane and rerouted into a wire, essentially. All right, so that's what it does. This membrane is the one that traps that electron flow. So let's look at that segment again.
Roots break down this organic residue. Electrons.
Yeah. Okay, whoops, too much. Let's go back a moment.
Residue.
The electron.
Area around the roots break down this organic residue.
There. Okay, so you see the generation of electrons there. And that is going to cause a flow, an electrical flow through the soil, which is hydrated. And you see that the plants, they keep mostly in water, right, to maximize the conductivity of the electricity. But it has to be trapped at some point with a membrane that will then channel those electrons, that electrical flow, electrical current, into a wire. Okay, so just the rest of it then.
Electrons are released as a waste product.
There.
An electrode absorbs them and generates electricity.
Zonnepanelen maken meer elektriciteit op een...
Solar panels are making more energy per square meter, but we expect to reduce the costs of our system technology in the future. And our system can be used for different applications.
Verschillende toepassingen op hetzelfde oppervlak kunnen combineren.
Plant microbial fuel cells can be used on various scales. An experimental 15 square meter model can produce enough electricity to power a computer notebook.
Little electric motors.
Onze technologie maakt ook elektriciteit.
Our system can be used for different applications. Our technology is making electricity, but also could be used as roof insulation or as a water collector. On a bigger scale, it's possible to produce rice and electricity at the same time.
That's on the rooftop.
And in that way to combine food and energy production.
En als we op een gegeven moment echt grootschalig deze technologie gaan toepassen, dan kunnen we bijvoorbeeld ook op hetzelfde oppervlak rijst produceren en elektriciteit.
A first prototype of a green electricity roof was installed on one building at Wageningen University, and researchers are keeping a close eye on what's growing there.
Okay. Any of you get the Dutch part of it? I did not. Thank God it was translated into English. Okay, now I'm trying to get out of here. Here we go. But it's exciting to see the creativity that's going on. With this energy from plants. There was another video, there are a bunch of these videos. There's another video that can teach you how to recharge your cell phone overnight with a plant, okay, from the soil in there. In fact, someone has commercialized it already. They sell you the pot that is all set up. You just need to put the actual plant inside, and it comes with a little port, an SUV port, where you connect the wire, the cable. So, I'm very tempted to try it. I'm going to try it and see how much of it, because with the cell phone, we can see by the number on the battery, what percentage, if it's actually charging or not. I'm very curious to see, and at what rate does it charge, right? Because it may take a week or so, which is not efficient. But maybe you put a whole set of plants. Exactly, the output. All right. Other aspects of creativity using solar or heat. Here we have we can either do passive heating in the northern part of the country by designing the house so that it has the exposure to the sun, right? What is known as a northern exposure, so that in the summertime, the rays do not come through the window. And essentially the window is in shade. But in the wintertime, because of the angle of the sun, the rays do come through the glass, through the window, and as the rays come through the glass and hit another surface, then that surface is going to heat up and it's going to generate passive heat inside the house. All right? And here they have an extreme where that heat is also collected in these coils that is used for heating up water, for example, to heat the roof. And there's a circulation pattern. In the summertime, the heat will clear out, heat rises. So the heat will get trapped in this part of the house, up here, up in the ceiling, high ceiling. And this is known as a clear story, right? That's a clear story. We'll have vents or levers where they can be opened to release the heat out to the atmosphere in the summertime. In the winter, you close this and trap that heat inside the house. So it's a design that could harness the light from the sun to turn it into heat, to heat the inside of the house. Conversely, to cool the house passively, you notice that it's pretty much the same design at the core of it. The center is the same design, the slanted roof with a trap, if you will, up here, an air trap at the upper part of the roof near the ceiling, right? Sorry. Okay. I forgot to turn on the other microphone, sorry. Anyway, you notice that essentially it's the same, it's a very similar design where the critical part is this clear story up here, right? That opens and closes depending on whether you want to keep the heat inside or release the heat. But there are two significant differences in the design of this house as opposed to this one. You notice that the edges here are much shorter on the winter house. Let's call this the winter house that is trying to harness heat, as opposed to the summer house that is trying to release heat. The extension of the roof projects out considerably on both sides to create a porch on both sides. Why a porch? Because then this is going to be in the shade. This air down here is going to be in the shade, and this air will be cooler than the rest of the air. And as that air circulates from the bottom part, from the low part, because this air up here will be hot or warmer, so there's a release there. The air down here will be cooler, and that is channeled into the house to create a current of air, cool. As it heats up, it rises and comes out here, and it will create a circulation. Whereas this air will start pulling, this hot air being released from the top, will start pulling air from the bottom, which will be cooler air, all right? So it's a natural breezeway there. The other thing is, you notice that the orientation is opposite. This house is oriented toward the sun, but this clear story is oriented away from the sun in the opposite direction, all right? So that the bulk of the sun over here is going to hit on the rooftop, where with good insulation on the rooftop, it will insulate out the heat, but also that can be used for solar panels because then you have more exposure on this side, all right? Finally, the last detail is this tree here that is very significant in the drawing, that is a deciduous tree, all right? Why is this a deciduous tree?
So in the winter, you get the more sun.
Yes. So Ed has said in the winter, you get the more sun. Why in the winter you get the more sun? What's going to happen to the leaves of this tree in the winter? They're going to drop, and you're just going to have those branches out there. So more sunlight is going to come through this tree in the wintertime than in the summertime.
Actually, Father, my backyard is like that. I have
Yes. Yes, exactly. Ed is mentioning that he did some planting like that in his home. And the backyard is oriented so that he has the citrus trees out there. In the wintertime, he's also a little further north, right? So they get, well, it's in the northern Florida. So they get more significant winter where trees will drop their leaves in the winter. Northern Florida, it begins there. Then into Georgia and the rest of the US, the citrus trees will drop their leaves. Here, the citrus trees, sometimes they drop their leaves and sometimes not, because it's a very mild temperature, right? But there, yes, they'll turn brown, just the branches, which allow the light to come through, heating up passively that section of the house. But in the summer, with all the leaves on, it creates a nice shade from the sun. Okay, so it's natural. It's a natural shade. A couple of other details for heating water specifically. There are either solar water heaters, okay, which are passive, energy-wise, or there are these new water heaters that are called tankless water heaters. The water heats as it goes through a coil in here that gets very hot. This does use electricity, okay? But here what you save is the big tanks and the rusting of the tank and all that. And I think that these are more efficient electricity-wise. They use less electricity per unit than the old water tanks.
They do, Father, because of the distance the hot water heater has to travel.
Yeah.
Okay. Okay, so there are a couple of ideas floating around. Ed is saying that the distance that the hot water has to travel is less, so there's less heat loss through dissipation, all right? So the heat is more efficiently used, the hot water. But also, people are saying that some of these run on gas, which is cheaper than electricity, okay? So these are some creative ideas that are being marketed already because there's a profit. That's all I have, basically. So bottom line is to put our creativity to good use, right? But thinking out of the box, as I say, to see how we can connect dots between different types of technology to produce something that is viable and then something that is profitable so that it can be sold in the market. Okay, that's all I have then for this lecture. We'll meet again next time on biodiversity. And then the last one, I would like to we have two more Saturdays. On the last Saturday, I would like to meet in person if possible. So an invitation for Ed and Gloria to come up and down to Miami to see if we can have a general group discussion and pull it all together with regards to the human population and environmental bioethics. Okay, so not next Saturday, but in 2 Saturdays. And what I like to do in anticipation, if you could start praying for good weather, the first part of that Saturday, of our last Saturday, I'd like to go to the forest for a while, a little bit, early in the morning or as we start, and then come back in here and finish our discussion here. Okay, so we'll do maybe about half and half, more or less. You're gonna be away, yeah, sorry. Right, the thing is that if we go to the forest, we're not connected there. Here we can try, even though we're in a circle, the sound is not that good because it's not, you can only hear me when I'm talking, okay? But I don't know what else to do really. But anyway, announcing it now 2 weeks ahead of time so you can plan accordingly. Okay, thanks again. And also Gloria and Ed, who have been remotely connected. I'm now going to end this recording.